Okay, good morning, everyone. So today we have this special session on the TEC, on the TESS Users Committee, that thanks to the organizers, we could have this big slot to have all of you participating and give us feedback. So we decided with the TEC to have a session with a few talks and then a lot of time for discussion. The first talk is on the introduction of the TEC by Dan Huber.
Thank you, Savita. Yes, okay. Okay, good morning, everybody. Thank you all for coming to this special session on the TESS Users Committee. As Savita already said, and I want to re-emphasize this, I want to thank the SOC and the TESS project for allowing us to have this slot. This is probably a first, at least in my memory, that a Users Committee during a science conference of a Kepler K2 and TESS mission gets an entire slot. I think it shows the value that the TESS project gives to interactions with the community. So I think this is a great sign, and hopefully we'll make the best out of this session. As Savita said, we'll have a few short talks from members of the TAC, both ex officio members and community members. This is sort of to kick things off and maybe spark some ideas that might later translate into the discussions themselves. But really, the goal of the session, and I mentioned this already yesterday, is to have interactions, and this session is really for you, the TESS community. So this will not be, lots and lots of talks, but hopefully a lot of discussion and back and forth. And really, we want to hear from you about how to make TESS the best possible mission for our community going forward. So we have a few ways that we will do this, and we thought about ways to facilitate this discussion. Of course, one of them will be just, regular comments and questions for the microphone, but we also have a way to anonymously post questions and comments through this QR code. So if you scan this QR code, it will take you to a website where you can type in a question or a comment, and we'll have members of the TAC monitor this. Melina in the front here will monitor whatever comes through, and we can then post these questions and comments for you anonymously. This QR code will be on the slides, most of the slides that you will see. So if you don't scan it now, don't worry, you will see it again later. So I want to start off with just a brief introduction into the TAC, the TESS Users Committee. So Avi has already shown this slide. We have 10 community members, 5 of whom are here. So myself, Luke Bouma, Savita, who's chairing the session, Armin Rest, and Melina Rice. The 5 other members are Marcel Agueros, Nora Eisner, Adina Feinstein, Teruyuki Hirano, and Krista Lynn Smith. You can see from the composition of this committee that it spans a wide range of science expertise, as of course TESS does, right? A lot of the TESS science is quite diverse, going from the solar system to extragalactic science, and this expertise is reflected within the committee. We also have ex officio members from the TESS project who are helping us, the community members on the TAC. So that includes folks from Goddard, MIT, and headquarters. I want to say at this point also a big thanks to the TESS project for all the support that they've given us. The community members in the TAC, I think it's been a very good relationship so far of them helping us do our job well in representing the community and making recommendations on behalf of the community of what we think the TESS mission should look like in the future. So some of you might ask yourself, what's the point of this committee? What do you actually do? And so to emphasize this, I thought I'd paste an excerpt of the charter, which is available online. In fact, all the materials that the TAC produces is available online on the TESS Science Support Center website. If you don't remember this link, if you just Google TAC, TESS Users Committee, it will take you right there. And includes the charter, and the charter includes this statement, which basically tells us what our goals are, and that is to provide broad-based inputs to the TESS project about the needs and priorities of the TESS user community, and to ensure that the interests of the TESS science community are served by the TESS project. So really, this committee is there as a liaison between the community, all of you using TESS data for science, and the TESS project, and we're representatives of the community that use TESS for science. So the committee was formed about a year ago, in May, June last year. We had some online meetings at the start. The first big milestone was a in-person meeting at NASA Goddard last November, where we got together and drafted our first recommendations to the TESS project. One of the outcomes of this meeting was the community survey that was drafted, and Luke Bouma will tell us a little bit more about the outcomes of this survey later in this session. We then took the output of that community survey and made a few changes, slight emendations to the recommendations, and then resubmitted them. And I'll highlight some of the main recommendations in a second, but one of the outcomes of these recommendations, for example, was the call for science pitches for the extended mission-free planning, and Allison Youngblood will tell us a little bit more about the outcomes of those later in this session as well. So just to wrap up, I will highlight 3 of the main recommendations that the talk has already made, one of which pertains to the extended mission planning. And one of the things that the committee felt very strongly about is to get the community involved in extended mission planning. So we recommended that the TESS project performs feasibility studies for non-standard observing modes. So what can TESS do that it hasn't already done? Right? It can't do everything, but certain things are feasible in terms of observing modes that it can do that it hasn't done before. And Roland will give us an update on these feasibility studies right after I finish. And then we, of course, had the science pitches, which was the second recommendation, which is to organize opportunities for you, the community, to express what do we think TESS should do in the extended mission free, and that was captured in the science pitches and should also be captured today. So if you have any ideas, you haven't been able to submit a science pitch, when you had an ideas in between then you can make that known today in this session. Okay, we also had some recommendations for the GI program. This is more specific to US-based users that ask for funding. So many of you will know that there was a threshold for new data eligibility. To be eligible to submit a GI program, it had to use 70% of new data. We asked the project to reevaluate and possibly lower that threshold. And we also asked to increase the period of performance for GI grants from 1 to 2 years. So both of these have actually been acted on, some of them actually independently for the GI program for Christina Hedges. The threshold is now at 25%. This might not be the case always in the future. So if you feel strongly about this, about what the new data threshold is for GI programs, then please speak up and let the TESS project know, because this is something that may change going forward. And for some of the GI programs going forward, we will actually have two-year period performances, even in cycle 7. And then finally, data products. This is a big sort of recommendation we deliberated on for quite a while, which is basically asking the TESS project to produce more Spock FFI light curves, right? So we heard from Doug Caldwell earlier that there's an effort to do Spock FFI light curves, but it's a limited effort. And we basically asked the project, we recommended that the project looks into increasing that, because we think that this is a bottleneck for the community to do science, to have really broadly available homogeneous FFI light curves. Of course, there are light curves available already from QLP and other sources, but having Spock FFI light curves is still something that we think would be very important. And we've noted that this may require shifting away resources from 2-minute cadence data, because there's only so much that can be done given the resources that we have. And this is currently being investigated, so there's no conclusion on this yet. Again, if you feel strongly one way or the other, you want as many Spock FFI light curves as possible, then please make that known, and you can do that today during this session. Okay, so that's all I wanted to say. There's more recommendations. The full set of recommendations is online. Again, here's the QR code to ask questions, give comments. So please use this session to provide your feedback to the TESS project and to the talk. And that's all I wanted to say. Thank you.
Thanks a lot, Dan. Okay, so if you have any questions, we have a little bit of time.
So we'll take a brief questions now after each of the small talks, but then we obviously have time during the discussion session as well. So that's how we envisioned at least how things will go.
Okay.
All right.
Seems that it was clear enough.
Okay.
Okay, thanks, Dan, again. Okay, so next we'll have Roland Vanderspek. I don't know if that's say it well.
Close enough.
So yeah, he's gonna talk more
about some other stuff.
About the EM3. Yes. Thanks.
Yeah. Good morning. I'm here to talk about the technical possibilities, operational and on the spacecraft. I'm going to focus entirely on that to the extent I can. I'm not here to give you my opinion on scientific merit. That's something that will happen later. So this is as objective as possible, although there's one suggestion based on what we heard from the community. We'll start right off with the 55-day sectors. As you know, as you can see here in the bottom plot, the goal is, the desire is to have to basically dwell on one part of the field for 4 orbits instead of just 2. Basically taking what normally would be a northern pointing and essentially skipping alternate pointings, but dwelling on the remaining pointings for 4 sectors. We just very recently, as in 2 days ago, got a preliminary report from Northrop Grumman. They had done an analysis, a thermal analysis of the problem, and they say, sure, you can go ahead and do 60-day sectors now, or 4 orbit sectors now. However, there may be an impact on the future, on the performance of the spacecraft in the future, particularly the thermal surfaces on the spacecraft. They're not sure whether the decay rate of these surfaces will be, how badly it will be impacted by going to 60-day sectors. So we could do it now, but there's some danger, well, danger is not the right word, uncertainty about what the future is. So a little bit more analysis will be required. Pointing possibilities I talked to on Monday. We have typically done pointings like this. We have our standard 54-degree pointing, 54 degrees being the ecliptic latitude of the center of the field, oriented north-south. We've done 40 degrees south. We've done 85-degree pointings where we move the fields up to avoid the scattered light, and we've done ecliptic pointings. It turns out, though, that we did that for scientific reasons. We have the flexibility to roll the spacecraft in angles such as this, as long as the center line of the long axis of the field of view goes through the anti-solar point at the middle perigee. We're good. I can say that again, but basically put a pin in it, spin it. You can't, it's all based on where the anti-solar point is at the middle perigee of, in this case, 2 orbits. So you can't just plop it anywhere on the sky. It is locked to the anti-solar point. So that leaves us with interesting possibilities. This is our standard 54-degree pointing. If you roll the cameras 20 degrees, you'll see that the fields sort of twist. And let me note that this hole here is not a hole, that's the CVZ. But this hole here really is, you're not looking at the CVZ anymore. As soon as you roll the field more than 12 degrees, you've lost the ecliptic pole. But some people want to do that. If you can push it further to 40 degrees, you'll see the hole gets larger, as it should. If we push the fields a little bit further north, we get away from the ecliptic, and the roll action is the same. The size of the hole is the same. You've just sort of lifted everything. You go to an 85-degree pointing. This is what has been called C3PO and is what we've done when we've lifted the fields. If you roll the fields 20 degrees and 40 degrees, you get this nice tight mid-latitude band. One advantage of the mid-latitude band, or one feature of the mid-latitude band, is that you'll get overlaps between adjacent sectors, and you will see, you'll observe fields out of the standard 2-year rhythm or 1-year rhythm. So these fields will be observed 2 or 3 months before the 1-year period that you otherwise would have. And we have some freedom to do weird stuff. This is nothing special. I just sort of eyeballed it and threw some graphs together. You've got different roles for different sectors, and different pitches in each of the sectors. I haven't really looked into this in great detail because, well, I haven't. And so I don't know exactly how much flexibility we have. There probably will be a dependence on ecliptic latitude. But if we're doing this, we're spending 8 sectors looking at that blob and not something else, but I'm not allowed to talk about that. We'll switch now to the idea of what can we do with targets, what can we do with cadence. Now, we can increase the number of 2-minute and 20-second targets. The impact of that is, as I mentioned on Monday, if we miss a contact, we lose more data, the fuller the SSR is filled. And you can see that on the bottom here. It's the same plot I had from Monday. If we're 55% full in one half orbit and the next half orbit, we will lose that little blob of data at the end. So we've lost 17 and 51 hours in the separate. If you extrapolate, say, okay, what happens if we fill the SSR to 75% full? We'll lose 4 days and 1 contact missed. And if we have 3 contacts missed per year, it's 2 weeks lost per year. But it may be worth it. 75% full is about 15,000 20-second targets. There's been discussion of adding a 2-second mode. That is possible. We've done it in engineering. It's not an official product. It would require work on the spacecraft side. And the other impacts would be, besides SSR fill, who's processing the data and where is it getting stored? So it really, every aspect of the ground system. There was a suggestion of changing the FFI cadence. In principle, you can shorten it, modulo FFI fill. The suggestion was based on breaking Nyquist, changing the Nyquist frequency of observations. I'm sure we'll get into that in a bit. Yes, it can be done. There's been an alternate suggestion made. We can do the same thing by just simply shifting the phase of the FFIs. The FFIs all start on a 200-second boundary in spacecraft time. We can shift it with a little bit of work, or we can randomize it. The value of that will be discussed later. And that's all I've got.
Thanks very much, Roland. So yeah, we have time for a few brief questions. I see a few hands
I'm sure
there.
I missed something.
Let's start.
Tara Featheroff, UC Riverside. I was really interested in the 40-degree tilt that was like 85 degrees offset. It looked like there was a lot of overlap of the sectors.
Yes.
How long is that kind of combined baseline? Is it kind of, it's not totally continuous, but it's certainly more than 2 sectors.
It seems, I'm just eyeballing it, quite frankly. It looks like 4 or 5 sectors. And I'm happy to go look at the plots more carefully. But I'm seeing 4 or 5 sectors of overlap.
Just to quickly follow up on that, I think showing cumulative distributions of choices and how many targets we get for more than 6 sectors, say, or how many we get consecutively for more than 6 sectors, or some number might be really useful for us to figure out.
Yep.
Yeah, since we get 13 straight continuous viewing zone targets, but that's a small sample size, we may get, with some pointing, lots of targets with more than 6 sectors in a row or something.
I'll work that up. I didn't have time before this.
Yeah, thank you very much.
Dave?
David Charity, next slide. Thank you, Roland, for doing all this work and all the people who worked on this. Can you say a little bit more, or can you eventually do the analysis so that you can later say a little bit more about the impact of the rolls and the scattered light and the orientation of the sun shields in each of the cameras, since they're not going to be in standard, operational orientation?
To first order, I think what we've seen in the past is the closer you are to the ecliptic, the worse it gets, especially in the north. If we roll, then the Earth and Moon are coming. I don't think it's going to be a significant difference, but I'm happy to think about it a little bit more.
Okay, I think we can move on. Thanks again, Roland. So next we have Luke Bouma, who's going to talk about the results of the community survey.
Thank you. So the point of this session this morning is for you to have a chance to tell the TESS project and also the TESS Users Committee how to make the most over the next few years of TESS. One way that as a committee we've tried to solicit that information was through this community survey, and I'm going to speak a little bit about the results. Dan already gave you the timeline, so just really briefly, after our first meeting we realized that we needed to conduct a survey. We distributed that survey through a few different venues. It was mostly email, Slack channels, and also through a newsletter from the TESS Science and Support Center. The survey ran for 5 or 6 weeks. We incorporated its results into our first finalized set of recommendations. And then earlier this week, Avi announced that we reopened the survey for a couple days, just in case you hadn't seen or heard about it before and you wanted to respond. So I'm going to talk about the finalized cumulative results from everybody who was able to respond. 160 people filled out this survey. So if you did, thank you. The majority of respondents, about 55%, were either at the staff or faculty level, about a quarter postdoc career level, and something like 10% graduate student or other. The majority of people who responded have been using TESS for a while, at least 4 years. Okay, it's 70% of the respondents. In terms of the science areas represented by the respondents, we let people check a couple different boxes for this question. So if we ask, what are your primary research areas? 70% of people said that stellar astrophysics was one of those areas. About half said that exoplanets was one of those areas. A few percent for galactic, extragalactic, and solar system science. We also had a question asking about involvement in various subgroups that are connected with the TESS mission. Just in order here, about a third were involved in the general investigator program, 20% with the TESS mission, about a third with TFOP, which is exoplanet follow-up, and a little over half with the TESS Astroseismic Consortium. Okay, let's talk a little bit about the pointing strategy, and then about the cadence, and then that'll be it. For the pointing strategy, we phrased many questions in terms of statements which people could either say that they agreed or disagreed with. So this particular statement is an example of that. The statement is that TESS should continue to observe the entire sky at least one time by the end of 2028. And as a reminder, by the end of the second extended mission, which is what we're in right now, the cumulative sky coverage will be 95%. So 95% of the sky will have been observed at least one time. The majority of people, in this case, strongly agreed that yes, TESS should continue to observe the whole sky at least once. Okay, there was a smaller slice of the pie that slightly agreed. And overall, we took this to mean that there's strong support for the idea that the next extended mission should include fields that haven't previously been observed. Next statement. So this one is about the extended sector duration that Roland was just discussing. So this statement was, assuming it's technically feasible, it's important that the duration of a TESS sector be extended beyond 1 lunar month. And in this case, we also had majority, supermajority, either strong agreement or slight agreement. So about 80% of people said that they agreed that it would be worth exploring the option of an extended TESS sector duration. You might notice, of course, that this is different from the statement of that this should be done. If there are any problems with the way the questions were phrased, for the pointing strategy, this one is very specific. I'll just say the way to read this plot is that if there's lots of blue or red, it means that there was lots of agreement with the particular pointing strategy. If there's orange, people are ambivalent. If there's lots of purple, it means that people disagree that this is a good pointing strategy. So the ones that I'll draw your attention to, on the far left, we have the all-sky observing strategy, similar to what's been conducted in the past. Some mix of northern and southern hemisphere, add a little bit of ecliptic maybe, include continuous viewing zones. There was also strong support for the idea that the gap in existing TESS coverage should be filled. Over here, we had a statement that the planned Plato observations should be considered. This was the statement that received the third highest favor. Okay, so some support, about 58% of respondents said that we should consider where the Plato field would point in the next extended mission. There was slightly less support, but still support for emphasizing the continuous viewing zones. Okay, let's talk about cadence and data products, and then I'll wrap up. So we've heard a little bit about the different cadence modes. Currently, there's 200-second full-frame images, 120-second cadence targeted pointings, and 20-second cadence also targeted. If we ask what TESS data products have you used and how much, the answer will probably not surprise you. Most respondents use the 2-minute data, 90%. Many also use full-frame image data. Now, this is kind of interesting because if you think about the selection functions of targeted pointings versus full-frame image data where everything is there, then the specific weights between these different data products are one axis of opportunity for thinking about what TESS can do in the future. So we asked this other question to try to drill in a little bit on whether the science that people were doing, or the science that people do with the 120-second cadence data is achievable with the 200-second cadence data. And it's not an overwhelming majority who say, yes, that's possible, but it is a majority. 68% say that they can accomplish comparable science at 200-second cadence as they can at 120 seconds. And if you consider the fact that there's probably an order of magnitude, if not more and more targets at 200-second cadence full-frame images, that was essentially the line of logic that yielded the high priority recommendation that the TESS project increase production and archival of mission-generated SPOC FFI light curves going forward. However, we're here for discussion today. So I'll go ahead, I'll leave up the conclusions. I'll say thank you to everybody who responded to this survey. And going forward, let's continue to figure out how to make TESS the best possible mission. Thanks.
Thanks a lot, Dominick. So yeah, we have time for 1 or 2 questions. There are any? Yes, George.
Yes. Yeah, just a point partially of clarification. The comment about the continuous viewing zone and Plato viewing, it should be clear that the Plato viewing zone is one of the 2 continuous viewing zones. It's the south ecliptic pole.
Okay, thanks.
Thank you.
Any other questions, comments? Yes.
Aviv from the Weizmann Institute. Just small comment. I think that going forward, it would be better not to give options, but of do you want to do this, yes or no, but to give trade-offs, because in real life, you always have to trade one thing for another. And I always want more and better for everything, but real life cannot do that in real life. So it's difficult to judge the answers when you don't know what you're sacrificing for them.
Thank you for the point. I agree that trade-offs are indeed an important part. Part of the point of this survey was mainly to gauge what people would like and to leave the trade-off to the TESS project for now to make that set of decisions. But I'll say that I summarized the things that are most easily stated on a presentation like this. There were also some longer form response columns, which we read very closely. The full set of responses are available on the links that Dan posted earlier. And we actually, in developing the recommendations, took both into account. Thanks.
Yeah, Armin, go ahead.
I think that was really interesting to see these tilted fields that basically give you more like 4 or 6 times the 27 days observing windows. And so maybe we have to pull the community, because the people that say like yes to the CVC, they probably didn't know that there's also an option to have this much longer times, not in the poles, but more in the normal areas. So just I think that's a very interesting option that I wasn't aware of, and I bet many people also didn't aware of, and that might be really popular.
Thanks for the suggestion. So if I understood the suggestion, maybe I'll just repeat it really quickly. New information can yield different preferences, as we've maybe seen in other areas recently.
Yeah.
Yeah.
Okay, thanks. I think we can move to the next talk. Thanks again, Luke. So now we have the last talk of this session before the discussion by Allison Youngblood, who's going to talk about the science pitches.
Here I am. Okay. Hey, everyone. So as Dan pointed out, one of the TUC's top recommendations was for us to provide an opportunity for the community to say their opinion about what TESS should prioritize in its extended missions. So they recommended maybe white papers, or maybe like the Roman mission did with science pitches. And so we really like that idea. Science pitches are 1 to 2 paragraph, low barrier to entry submissions, describing what science would be enabled by some kind of change, or maybe even just keeping the status quo. And so here's my timeline to give you a sense of context for all of this. We received the TUC recommendations in mid-December of last year. We released a draft call for the science pitches in the early spring to give the community a heads up that this opportunity was coming and give us more time to do our homework and create this extended mission planning guide that we ended up releasing along with the final call for the pitches. So you can read the final call at the link below. And we advertised this as widely as we could. We advertised via the GI website, the newsletter, the PAG mailing lists, the Inspires mailing lists, as well as relying on our networks, including the TUC, to help us distribute this call. So we had a submission deadline in mid-June that we ended up extending to June 21st. And then over the past month and a half, we've been reading through the submissions. They've been really great. So here we are today to discuss them. We've been looking forward to this opportunity to engage with you all. And we just found out fairly recently that the senior review proposals, this proposal that every NASA operating mission has to submit every 3 years to continue in a new extended mission. These proposals are due in mid-December, so we have just over 4 months between now and then. So what we've done, we assembled a team of science and engineering leaders from across the mission to help us sift through submissions. Our goals were to identify common scientific and operational themes and synthesize some options for operation strategies that would maximize science return. So we met twice over the past month and a half and have been very much looking forward to the discussion today. I want to emphasize that there are no winning or losing science pitches. We were really appreciative for everybody who took the time to submit their ideas, and we read them with great interest. So we received 26 science pitches in total from 26 people at 25 unique institutions across 3 continents. The pie chart shows the breakdown of topic. Most submissions were about exoplanets, then stars, then some were other or multiple topics, and 1 solar system submission. I want to note that this pie chart is the balance between exoplanets and stars is a bit flipped from TESS paper statistics. Approximately 60% of all TESS publications are about stellar astrophysics, with only 40% about exoplanets. So the sub-bullets give you an idea of what some of the subtopics were in all of these. This is a fairly exhaustive list. So regarding the operational themes that we noticed, half of all pitches address the sector durations, with most calling for longer durations and 2 calling for keeping them as they are right now. Some reasons given for longer sector durations include longer period planets, eclipsing binaries, better flare statistics, better rotation periods, you name it. A third of pitches addressed cadence and/or data products, with 3 calling for keeping things mostly as they are. 3 were about reducing aliasing. So 1 was about adjusting the FFI cadence to improve the Nyquist limit. Others were about adjusting how often we visit a hemisphere or how often we do momentum dumps in order to improve this. 2 were about increasing fast cadence slots or introducing a faster 2-second cadence option. And so some reasons given for this include astroseismology, stellar activity, as well as improved transits for bright stars. 2 pitches emphasize the importance of self-consistent data processing for the best exoplanet transit parameters. 62% of pitches address pointings in some way, and some factors given where, like certain open clusters are in this part of the sky, make sure to capture those if you can. Synergy with multiple observatories, including Kepler, Plato, and Rubin, were emphasized by several pitches. Some really emphasized how important it is to obtain 100% sky coverage. Others advocated for focusing on an individual hemisphere because of the presence of certain RV capabilities in certain hemispheres. And a few pitches were really focused on, like, please make sure you capture my favorite star for this important reason that's previously been unobserved. Okay, and then my last sub-bullet that I want to emphasize, there were a bunch of pitches about focusing on the ecliptic poles, but there was one pitch that stressed the importance of gathering longer stare durations at middling latitudes, and that was for exoplanet science. So the team, we assembled some options and some themes. So there are 3 themes: sky coverage, pole centering, and sector duration. There's an A and the B option here. These themes are fairly independent of each other, so we can mix and match. And the options are a little vague at this point because we don't want to over-constrain the problem right now. We do have some flexibility. And I'm showing this figure again, which demonstrates pole centering option B, the C3PO, where camera 3 is centered on the pole. And you see in the northern hemisphere, this is the status quo 27-day sectors. And on the bottom is the longer 54-day sectors. So to summarize our discussion that we had internally to the team, so there were some things I wanted to convey. Make sure I remember. So there was a sense among the team that it would be advantageous to shake things up for the senior reviews for TESS to remain competitive there. There's a slight concern, maybe about, like, is there diminishing returns from exoplanet science or decreased community engagement if we continue with operations as they are now? We don't know, but that's something that we're wondering. However, on the other hand, some of these operational changes can be quite taxing. And I think, as you all have heard repeatedly, we're in a very restricted budget environment. So it may be difficult for us to implement something new and different. But so to summarize our opinions quickly, so for sky coverage, there was no consensus, but we've heard great arguments for why TESS should focus on all sky science, as well as for why it should focus maybe on a single hemisphere plus the ecliptic plane. For the pole centering, I think that folks were intrigued by option B, to shake things up. However, again, that and also data quality with reduced scattered light is better near the poles. But of course, we definitely do want to observe the ecliptic plane, I think. And finally, sector durations. I think that was the thing that there was the most kind of consensus on, or because we've heard very clearly from you all through the science pitches, through your talks, through your papers, that longer sector durations are desired. And so Roland nicely summarized where that analysis currently stands in our ability to do that. Okay, that's all. Thank you.
Thanks a lot, Allison. Okay, so we have some time for a few questions. No? Okay. Oh, one there. Okay.
Hello, I'm Damoto from the University of New Mexico. I'm wondering about like the prospect of keeping the timing of the sectors closer together, because like right now there's this big 2-year gap between successive sectors. And I'm no expert, but I get the sense that like decreasing that time in between successive sectors is also of importance. So I'm wondering like where that kind of fits into these.
Oh, yeah, so it's not explicitly mentioned here, and there was at least one science pitch about that, about, maybe don't wait 2 years before revisiting a hemisphere. Is that what you're saying?
Yeah.
Yes, at least one person advocated for that cadence could be changed. So I guess where that is here is that we could spend all of EM3 essentially focused on a single hemisphere, so that we tile it out and then we come back again. So that would shake that up. So you're right, it's not explicitly here, but that is something, like I said, we're trying to keep this vague, so there is room for that kind of suggestion, absolutely.
Thank you.
Okay, no other questions? Okay, then I guess we can thank Allison again. And we start the open discussion.
Okay, so we're going to swap over now to the discussion session of this TAC session. So basically, this will be open for discussion. We have TAC members with microphones, armed with microphones, who can run around and pass on the microphones for anyone who has questions. We have a few, hopefully what you've heard just now, hopefully sparked some ideas or questions you might have, or comments you might have, or comments you might want to convey to the TESS project about preferences that you have of what TESS might do in the extended mission, or any aspect actually of the TESS mission. But just to summarize, right, these are some of the topics that we can discuss. This is a non-exhaustive list. Obviously, the important one coming up, as Allison just reminded us, quicker than we thought initially, is the extended mission, right? So TESS, the TESS project will soon be working on the extended mission to senior review proposal. And so the input from the community is very important for this. And there's already been ways to provide input. But today is another, and this week is another opportunity to provide input about this. So where should TESS point? For how long should it point? What are the things that the community values? But we can also talk about other things, general tools and data products. That is, of course, in some sense also related to the extended mission proposal. Do we want 2-second cadence data? Is that something, it's a possibility, as we've heard. Is that something that is important to our community? Do we want more 20-second cadence slots? Do we value the 2-minute cadence slots? What about the FFI cadence and so on? The GI program is, of course, also another part of this. So any topics related to the GI program, for the US-based investigators, the funding opportunities that are there, the current strategies, or the small program, the mini, small, large, and key projects, is that something that the community is happy with? Do we want more large programs? There's various variations to this that we could discuss. And then there's a whole range of other topics that we can discuss related to data accessibility, diversity, equity, inclusion, accessibility, the TY catalog, the TFOP program, ExoFOP, ROSES, which is the funding opportunities, of course, or also how the data is being archived, for example, at MAST. So all of this is up for discussion. So if you have any thoughts about this, please raise your hands or submit your questions online through the QR code. Again, you can do this anonymously if you'd like, but I'll open up the floor for discussion. This is sort of the prompts that we've had. So we'll see. Start with Dennis. Yeah.
Dennis Tello from Sydney. I've already talked to Roland about this, but based on his talk earlier this week, I thought, would it be possible that we make better use of data storage? Because most of the time, 45% is empty. And so could we have a second tier target list that we would basically fill up, not necessarily the full 45%. And then in the case we miss a downlink, nuke that data. because if we don't miss a downlink, we have that extra data. And the obvious thing to put into that kind of extra slot would be the 20-second data, because we know it is better photometrically. So we could have some, say, a magnitude limited sample of all stars brighter than X go into that second tier data set. And that would be good for the entire community.
Yeah, so perhaps I want Roland. Yeah, Roland,
I'm
to that.
I'm going to pass it over to Ed Morgan in just a moment. I'll say the word flight software change, and then.
Yeah, it would be a flight software change, but it's not a terribly difficult one. My experience, whenever we talk about this, we have a great difficulty. It's hard to separate targets. I mean, you can prioritize FFIs over 2-minute targets, but you can't specify particular targets over other ones because it's all in the same files. I don't see any way to do that.
But is cadence possible? I guess that was the suggestion.
Cadence, but my experience is that people can never agree on which cadence is most important. So we can certainly do cadence. We can try and put low priority on FFIs with straight light, a lot of straight light. You could do that. So things we could.
John Jenkins at the SPOC at NASA Ames. There are also downstream effects. We're still struggling to deal with the data gaps that are introduced and lost data because we often miss passes and we fill more than half. And so there are operational impacts as well that would need to be considered.
Maybe one of you can remind us how often the downlinks are missed. It's not very frequent, is it? Maybe Roland actually mentioned this in his talk, and I forgot. The downlink, like missing the pass. So how often it's actually
It's about
missed?
2 or 3 times a year.
Okay.
I was going to quibble with the word often that John just said.
Right. Okay.
But it's seriously just 2 or 3 times a year.
Yeah, Derek.
So Roland, you'd also talked about improvements in lossless compression with GZIP, et cetera. I mean, to what extent do you foresee that addressing this issue? Because that could be another solution.
I'm really glad Ed's sitting behind me because he's the one driving the GZIP work. So.
Normally, if there's no stray light, we do extremely close to the optimal compression right now. We're getting the data down at 3 bits per pixel, which is incredibly good. If there is stray light, our normal compression scheme breaks down, and we are working on implementing a scheme where we just gzip the files that are huge because of straight light. The gain is not huge. It's a few percent, maybe 2 or 3% of the SSR by doing that. There's not that much stray light. But.
Okay, yeah, in the back.
Kirill Sokolovsky, UIUC. So something like half of the mass of the Milky Way galaxy is located on our sky within 10 degrees of the direction of galactic center, basically the bulge. So this is like a hot spot for everything stellar astrophysics related. But this region of the sky is only to be observed for the first time by TESS in one of the upcoming sectors. So my question is first, why is it the case? And then maybe it is the spot that is worth observing more. Thank you.
So I guess this is a question. So if I summarize the question, so there's a particular part near the bulge, I guess, that's now being observed for the first time in TESS. And the question is why did it take so long for TESS to get there?
Basically, yeah.
So I'll hand it over to Roland in terms of pointing strategy, but basically, I mean, I think part of this is that TESS is just finishing up. Well, I don't know at which percentage we are at the end of EM2, but
yeah, I'm trying to map the hole in our map because of the scattered light with the galactic bulge. Luke, do you know this offhand? Are we, is the zone of avoidance right over the bulge? The zone of avoidance is right over the, we'll get to it next year. And we could have before, but it would have been really ugly as far as scattered light goes.
So this is one argument towards, observing the whole sky and filling gaps, of which, can you remind us actually, Roland, how many gaps are still left after EM2?
It's just that one gap, and we should, I think, again, now I get to have a preference. One of the first things we should do in EM3 is just fill in that hole, and it should be straightforward to do. Yeah. We'll do there's that little strip on the ecliptic, which we'll do in year 7, but there will still be a little 5%, 4% box that we need to fill.
Yeah. Yeah, here.
I'm going to maybe give my perspective. From the exoplanet side on the pointings, I feel like TESS is the only mission capable of finding some of the most interesting targets for JWST, the kind of small planets that are really being observed in transmission spectroscopy right now. And obviously JWST can observe the whole sky. And I think it would be a real shame if there were key targets for transmission spectroscopy that only TESS could find that we don't find because we concentrate on the poles, or we don't observe at long duration in the middle and low ecliptic latitudes. Because at the moment, most of the planets at 50 days, TESS hasn't found them because they're not at the poles. So I would really think that if you could trade time in the continuous viewing zone and move it to places where TESS hasn't yet observed for longer than 27 days, that would be really useful for providing these missing candidates for JWST transmission spectroscopy.
Yeah, George, and then I think Malina has her hand up too. Yeah, just keep speaking.
Okay. I think it's really important to keep in mind that the continuous viewing zone for TESS is the same as it is for JWST, as the same as it is for Roman, and that that will also, because it's at the north or south ecliptic pole. So that's that the last comment may have muddled that situation a little bit.
Well, maybe I'll give you an opportunity to clarify. So I think it was, well, yeah.
I think we found everything there. Everything that's not to be found, that's not already been found in terms of exoplanets in the CVZ is either very small and rocky, which probably won't have an atmosphere, or it's at very long periods, which we're hitting the geometric transit probability. There might be a few planets to find. So everything that's good for JWST, TESS has already found in the poles. That would be my my kind of understanding.
So the goal would be to find the longer period planets further away from the ZVZ, for JWST.
Yeah, John Jenkins at the SPOC. Just comment on detecting planets. So if you had 13 sectors of observations, but you spread them out over 13 years, you'd find far fewer planets than you would if you had 13 sectors in a row. So the best way to fill in, actually, especially mid-latitudes, would be to increase the sector duration. That gets rid of a lot of the period aliases, finds a lot of the companions that are playing hide and seek. And it's just that when you spread out the observations, you actually decrease your sensitivity to those planets because you're increasing the number of effective statistical tests you're performing because of the way that the period telescoping works. Anyway.
Okay, yeah, Karen.
Hi, Karen Collins, CFA. Would it be possible and would it make sense, this is back to the memory storage configuration, to increase the cadence of FFIs to fill the memory as much as it can be filled? I don't know if that's 85% or 100% for one sector. And then if you miss the next sector, instead of, if you miss the downlink, instead of throwing away the entire sector, interleave the images and you reduce the cadence by a half, but you still get both sectors at the next downlink.
I see Roland struggling.
So only 2 or 3 times a year do you get the reduced cadence.
Do you want to respond, Roland, or think about it?
Yeah, I think I need, I can go and step aside with Karen and she can say all that again. Didn't quite get it. If you want to try again now, yeah, probably. You know, in principle, changing cadences and dwell times and so on between sectors is possible. It's not fun. And I'm not sure whether, it's certainly not optimal, but given the science case, we can certainly look at it. But let's talk offline.
Okay, I want to make sure that Melina gets the question from online as well. Let's start with that. Maybe, I don't know. We have too many mics, maybe.
Is this one? Okay, yeah. This one's working. So the first one is, could the project update the tick with Gaia DR3 or DR4 when it comes out?
Yeah, good question. So maybe someone from the project, I guess actually that goes back into how the tick was produced at the start and plans for updating it. I think it came up already. Maybe David, finger pointing on the project. David can respond as well.
So right, we put the tick together at the time, to serve the purposes of the prime mission. Truly, we definitely realized there's a lot of information out since then. Oh, by the way, sorry, I'm Joshua Pepper, NASA headquarters. So we definitely realized that there's a lot of information out since then. New releases from Gaia. There's other all-sky catalogs, and there's probably procedures that could be used to better formulate the composition of the tick. That was done, in preparation for the prime mission, and it is up to the mission itself to decide if resources would best be spent on an effort like that to create an updated tick, or this is up to people in the community if they would like to submit proposals to do that kind of work to be peer reviewed by a NASA review panel. Yeah, we'd have to think about how we can advise about what would be an appropriate solicitation. I'll get back about that.
Okay, so to summarize, right, if this is important for the community, one way to get it done perhaps is to write a proposal to get funding from NASA for the community to do that, but it's unclear which call that would go towards. David Ciardi had his hands up.
Yeah, so David Ciardi, next slide. So this actually brings up an interesting overall topic, which is most of this session has been organized around operational procedures for the spacecraft, and that makes sense, right? That's the hardest thing to change. But I brought this up in previous times and in different contexts, but I'd like consideration for the project to think through in the extended mission proposal about products that they would like to see to come out of this. And so this new tick idea, for example, that's one piece of starting to think through a good, final, reliable, nearly complete catalog of exoplanets, right? One of the legacies of Kepler was a catalog of candidates that we believe in a variety of ways, for a variety of reasons, in a variety of ways. And so I think the TESS project has done a wonderful job of producing candidates, but at some level it's been piecemeal. We've learned more information since that time, and so I think it's not unrealistic was the phrase I was going to say, but ignore that word for a moment. But I don't think it's unrealistic to think through a final good legacy product of a catalog of exoplanets, built on Gaia DR4, DR3 properties, built on the entire suite of data that the TESS mission has collected from the prime mission through all the extended missions. It's that kind of idea to think through, and it relates to this idea of the tick, a new tick. And then sort of completely unrelated to what I just said, I would like to also, for the community and the project to think through, the continuous viewing zones sound great until you recognize that their declination is at 66 degrees. And it's actually quite difficult to follow them up in general from a lot of observatories, especially ones that are located closer to the Earth's equator, because the air masses become very high. Mid-latitude pointings are actually much more favorable to general follow-up from around the world and around the community. And so I understand I'm totally in favor of longer period planets, but the ZVZ is actually one of the more difficult areas to do follow-up from the ground.
So just to clarify, I think the suggestion was not necessarily to stay at the ZVZ, but find longer period planets outside of the ZVZ and adjust the pointings that way. So I see a lot of hands. Maybe we can, anyone who's related to what was just brought up. So TESS products, Jesse. Yes, should stay a little bit on topic, but don't forget the question.
So it's probably no surprise what I'm going to say. If we're getting diminishing returns from individual planets, we can study planet populations and do demographics. But that would be in line with what David is saying, the project putting out products that you can do demographics with, right? Like a uniform list of TOIs that's not manually vetted, completeness and reliability information about the TOIs, that kind of stuff. There's products the project could be making that the community could do demographics with. And I think if we're looking for exciting new pivots in EM3, demographics is going to be huge. Like when we have this final catalog, people are still publishing Kepler demographics, and Kepler's been gone for a while. So demographics.
So maybe as a follow-up to this, so in terms of products, but in terms of observing strategies, is there anything that would go towards that as well? Or is it mostly just using the data that's already there, right?
So that whatever we choose in EM3, we can use with the others. Yeah, so whatever observing strategy we choose, just make sure you can analyze it. So yesterday in the demographics session, Michelle was talking about LEO being able to handle multiple cadences because of the multiple different uncertainties. So having cadence agnostic pipelines and information would also be good.
Okay, more comments on tools and data products, Dennis.
So mine is actually related to the comment before, but I got hijacked. So the one that Josh talked about. Related to that, could one maybe see, I don't know whether it's the DGI office that could do that or where it sits, but some sort of an easy to use online tool where people can easily translate tick IDs to Gaia IDs from all the Gaia DR2, 3, and 4, whether it's a single target or a list. I think many in the community would like that. Hands up if you like it.
Okay, so currently the tick can give you DR2 IDs, but you're saying you want the DR.
Exactly, we want it up to date.
Yeah, okay. Is that Christina in the back? Yes. Okay. Maybe Christina wants to respond with it. It's part of GI territory.
Thank you for the hands up. That helps. I think I'm hearing Dennis just to check. Instead of a tick version 8.3, you're saying just give me a tool that can convert between a tick ID and a Gaia ID, or a Gaia ID and a tick ID, so that you can have like, here's the DR3 version of the tick, and you've got your hands up, and that's, I was actually other hands up. Okay, all right, I'll keep that in my back pocket. Oh no, I'm not saying that I can do it. I'm just saying that that's different to making a tick 8.3. No, I don't. No, I think I do realize how hard that is. I'm not saying that I'm going to do it, but I do understand what you're asking is not the same as I want a new catalog. Okay, but I have a new topic, a new question.
Okay.
Roland brought up cosmic rays earlier in the meeting. In the prime mission, we had 30-minute FFIs, and we have a cosmic ray rejection, which takes the data and basically throws 20% of it away. People in this room know that that does change the precision of the data. It also changes the error properties of the data. It changes the distribution of the data. Now that we're on 200-second FFIs, is this as relevant? Spock 20-second products fix cosmic rays on the ground, and so don't need an onboard algorithm to do this. My question is it possible to have Spock FFI light curves at 200 seconds when natively on board there is no cosmic ray rejection and it's done on the ground, and whether people want that because it should increase precision and it should make the data noise properties more uniform? And I don't think it changes anything about storage on board, but Roland and John, maybe tell me I'm wrong.
Yeah, so maybe we'll have some comments from Roland and John about feasibility, but I think this is a very good topic that I'd love to hear, and I think the talk as well would love to hear more community input on exactly what Christina just said. The Spock generated FFI light curves, and the cosmic ray rejection is that's a good point. Yeah, so John.
I hope that's good. Is it on? Now it's off. Hello.
Keep it on, please. Yeah, look.
Is that it? Oh, wow. Okay. Okay. Got it. Okay. All right. So the way that we do the cosmic ray rejection at 20 seconds is going to be very difficult to translate to the FFIs unless we're talking about the Spock FFI light curves, because we use quaternion information to predict what the pixel value should be. And then we condition the detection of cosmic rays in the photometric aperture that we've chosen as in terms of whether they appear to help or hinder the noise properties of the light curve. And so one would not expect, if we apply the algorithm without that conditioning on a flux estimate, to not be it just won't be as effective for FFIs in general. But it's also the case that Zach Berta did studies before launch as to where the break-even point was on whether onboard cosmic ray mitigation was better than doing it on the ground. And the break point was at about 2 minutes. So maybe that's changed in light of the fact that the cosmic ray mitigation on board is being flummoxed by some of the modes in terms of the pointing that's going on. And so most of the cosmic ray mitigations on board are actually removing samples that represent modulation of flux by pointing induced behavior, not by cosmic rays. And that's why we do a much better job on the ground with the 20-second data. We're looking at updating the pointing algorithm on board, and some of that behavior may change in ways that we don't fully understand now and may impact the reliability of the cosmic ray mitigation on board. The other comment I wanted to make a long time ago is that it was a really big deal for us to convert from TIC 7 to TIC 8. We went back and we reprocessed the year 1 data, and any target that was deemed in the updated catalog to be an artifact, we abandoned. And I'm in favor of it, but it's a big thing in terms of operations if we want to bring the historical data products up to snuff with the new catalog.
Okay, I want to. There's one question online, and then we'll go to Keaton. That's I think related to this that I saw, which is would space on the solid state recorder, I think that is, how much space would be saved by dropping the 2-minute cadence targets completely, and how would this affect the analysis effort by the mission? So in terms of trade-offs, if we would not
6 to 7%.
60?
6 to 7%.
6 to 7%.
Not a whole lot.
Yeah.
20-second and 2-minute are about 7 to 8% apiece.
So it's mostly the FFIs take up.
And this is 7 to 8% of the data collected on the ground, of the data collected, not of the SSR. So 3.5% of the SSR per half orbit currently.
Okay. Okay, Keaton had his hand up first, so go over to the left. Oh, right.
Hi, Keaton Bell, City University of New York. Roland wanted me to bring up my suggestion to change the FFI cadence to potentially reduce Nyquist aliasing in revisits from 200-second FFI to a potential 220-second or 180-second FFI. The idea is with 200 seconds, if you don't know that physically your signals are going to be longer than 400 seconds, you need to be worried that you might detect an alias, get the measurement of the periods wrong. Or if you have eclipsing binaries or transient exoplanets with periods that are very close to a multiple of 200 seconds, you get the same phase information each time there's a cycle. And if you were to change the FFI cadence slightly, then say by 20 seconds, the revisit data product, 200-second light curve, then later a 220-second light curve would have the same Nyquist limit of the 20-second data products for the full frame images where there are revisits. I think that's an interesting signal processing consideration. I don't have a super strong science case to motivate such a change. But I want to bring that up in case there are people here who are like, I want to do FFI science on rapid variables where this would really make me maybe not need to propose for the 120-second or 20-second data products. Since those are now oversubscribed, that might have some value.
Okay, anyone want to respond to that? Responses to that comment? George?
One of the concerns I think about going to something like 180 seconds or 220 seconds is, as things stand currently, if you're interested in working with the previous 6 years of data, 200-second FFIs, 600-second FFIs, or 1800-second FFIs, the faster cadences can simply
I think the microphone is, hold it further up at the start, but I think, oh, maybe. Other mic, I got a microphone.
Okay, all right, thank you. I think yes. That's much better. Okay, I think one of the concerns with going to the 120, to the idea of 180 or 220 is that if you want to utilize the previous 6 years of data, which have 200 seconds, 600 seconds, or 1800 seconds, if you're working with those, with the previous 6 years of data, the shorter cadences can simply be added together to match the, whatever you wish for a longer cadence. If you brought in something that was not an integer multiple, I think that would mean it would mean that you couldn't use the at least in a convenient way the data from the previous 6 years. But I could be wrong about that.
Right. Okay, a response to that comment as well? No? Okay, John, and then we'll go back to the...
Yes, so I want to thank Keaton for bringing this idea to us. I've been looking at this, and the problem really isn't the cadence, it's the sampling. So yes, 220 seconds would significantly increase the effective Nyquist limit, but so too would injecting offsets in the start of the cadences. So what we've attempted to do through flight operations is manage the start of the cadences so that, at least in the spacecraft time, the data look like an evenly sampled time series. And that permits one to use FFT-based techniques to analyze the data and conduct planet searches, which is what we do at the SPOC. On the other hand, when you think about Kepler, the typical barycentric time corrections over a year were plus or minus 6 minutes, which was a small fraction of the 30-minute sample rate. We can tolerate small changes in the phase of the 2-minute data. All it means is when you fold the data, pretending the data are evenly sampled, the transits are not quite perfectly lined up, but it's a relatively small effect. And when we do the model fitting, we're fitting in with the barycentric time correction, so it doesn't matter at that point. So I've looked at this, I've got a model, I can sit with anybody and show them that if we injected small, like plus or minus fifth of a cadence offset, that we can increase the Nyquist rate. So that'd be once per orbit. And if we do it every half orbit with 4 offsets, we can get similar results to changing the cadence to 220 seconds. The other thing is that requires the signal you're looking for to maintain coherence over the interval between and through both sides. Otherwise, it doesn't do any good. If you only have a sinusoid and one, it doesn't do any good to have any more data beyond that. Or if the phase changes, it's going to somewhat destructively interfere. It's not going to build by the square root. So there are other considerations when one talks about P modes. They don't maintain coherence over timescales of years. So at any rate, I think there is an alternative that we could implement that would not dramatically impact our software or operations. And I'm happy to discuss that with folks.
Okay, so we had a few hands up in the back, Tansu and yeah.
Thanks. Tansu Dailan, Washington University. So speaking of cadences, it was also mentioned that there's the potential of 2 seconds. A couple of questions come to mind. First, how many targets should we expect at 2 seconds? How would they be selected? Would that be part of the GI process? And maybe last, what kind of systematics should we expect in that kind of data? Because it's already used for, as part of the control loop. So I would assume there could be some systematics that are not very familiar at longer cadences.
Yeah, I think the microphone is in the right area to get the questions answered, except for the GI program. I guess Christina is over there. I'm not sure if that's ever actually been discussed, but we can have Roland or John weigh in, or Allison. What is the plan for the 2 second cadence? If there's strong community support, how would it be implemented? How many targets?
Well, Ed Morgan told me today that we could collect data for about 200 targets. But it does require a software change because if you're collecting the 2 second data on a camera, you can't be formulating the quaternions without a software change. Okay. The other thing is that we can't collect the same kind of collateral data that we do. And so at 2 seconds, the systematics are going to be different. We know that we see jumping behavior, kind of erratic behavior in the black levels, and that's going to be different. If you don't collect sufficient collateral data, you're going to be having to live with some of those things. So without at least some experimentation, and it's not clear to me that we could actually get a significant benefit out of the 2 second data because of unresolved systematics that would be different from those at 20 seconds or 2 minutes, which we understand much better. So, whoops, I think it's risky.
I presume the mechanism for proposing the targets, and people can correct me if I'm wrong, would be for the GI program, because all targets that are observed need to go for the GI program. So presume that would be the way to do it, but folks can correct me if I'm wrong. Yep, Allison gives a thumbs up, so. I don't know if you see the same thing that I see.
Just on the 2 second data, we did take 1 sector's worth of 2 second data, and we have it in TPF format. We could distribute that to people if someone wanted.
There's test data. There's the data already taken. Yeah. So this was actually a comment by Connie Ertz. She's not here today, but she sent that to me, which is that if there's data already available, I think if that could be made public to the community, I think that the community could look at it and maybe inform the test project whether that is something that's would be good to have more on other stars. I'm not sure how feasible that is, but that would be one. No.
It's not calibrated, and we took it in order to measure cosmic ray.
Okay.
I'm not sure what the distribution of stellar brightnesses will be in those 170 targets. So.
Okay.
Okay.
That sounds useful.
All right. So it reminds me it's evenly distributed between, say, 4th and 18th magnitude and 170 targets. Yeah. So.
Okay. Okay, let's go to the left. JJ.
I want to go all the way to the longer cadence. I like that the TUC recommended more mission-generated Spock FFI light curves, and I think that would massively benefit the community. My question is, how much resources would be required to make community-generated Spock FFI light curves? That is to say, totally port the software and the tools needed to make those light curves, since there is a limited amount of computing power. Many of us have very faint targets that will never get Spock FFI light curves unless we generate them ourselves. Yeah, how many resources would be required to make that change?
John.
Well, we open sourced and released the Kepler Science Operations Center code. The pipeline infrastructure is in Java. Most of the science code is in MATLAB. I don't think anybody's actually used it because you would have to build new interfaces, because that system was built on top of a custom time series database that you'd have to recreate. And I think that's the biggest block, not the MATLAB itself. We'd have to port, we do have a grant that some of us are working on to reprocess the Kepler data and improve the pipeline. And the first thing we're doing with the 2 postdocs who just arrived on May 1st is to port the Kepler pipeline to Python. We plan on releasing that, but it would be a big effort to port the code to Python. Potentially, I suppose, because we use compiled MATLAB on the supercomputer, that we could containerize it. But I think that would be a big effort. So, and the other thing I'd say is that we've been looking at the options for increasing the number of FFI light curves. The resources we've estimated would be a small fraction of our current budget. So I think that's likely achievable. It depends on the details of our budget for next year. And the resources we have for compute are quite modest compared to the resources available at the supercomputer. So for example, our allocation this year is 200,000 standard billing units. That's 200,000 compute hours on a standard Broadwell node. In 2021, the supercomputer pumped out 100 million SBUs, and that's gone up considerably since. So I don't think it will be a problem for us to request additional SBUs. The changes that we need to make in software would allow us to gracefully scale up the production of TESS FFI light curves. I can't say what the limit is, but it would be easy to scale them up by a factor of 2, 4, or something like that. And then beyond that, we have to look at the resources that we would be granted to do the processing. And we've got estimates for the storage that we would need, that sort of thing.
Okay, I want to get to the last question we have unanswered that's online, which is probably a question for David, CRD or Jesse. How can ExoFOP serve as a database for a list of published parameters for non-TESS systems? And what's the best way to advertise this to people outside of TFOP? Or does ExoFOP already include non-TYs? Is that? How can ExoFOP serve as a database for a list of published parameters for non-TESS systems?
So Jesse should weigh in here too in case I missed something, but the ExoFOP is built on the entire TIC. So anything within the TIC, any star, which is built in Gaia DR2. So every single object is already there. We're already working to expand the ExoFOP's ability to handle specialized target lists. So for various missions and or for users and groups to be able to create their own lists. If there is something very specific in that, whoever asked that question, if they want to contact me or Jesse, we're happy to address it. It does not contain extragalactic objects unless an extragalactic object happens to be, Gaia sees galaxies and therefore it's in the TIC, that kind of idea. But it's not. So Jesse, am I missing anything?
Yeah, it has Kepler and K2 included, so that's what I thought.
Oh yeah, right. So we've already combined this with the Kepler and K2 candidates are there. We're going to allow, we already allow people to upload their own CTOIs, but we're expanding that to be generic candidates as well that you might want to share with the community or follow up. So for example, if you found a radial velocity candidate that doesn't transit, right, it's that kind of idea. So we're moving the ExoFOP to be more generalized in that sense. It is slow. We don't have a lot of resources to do all of this, but that's where we're going. So yeah, please feel free to reach out to Jesse or me, absolutely, if I've not answered that question to your satisfaction.
Okay, thanks, David. So we have only 5 minutes left. So I want to encourage comments for a few topics that we've talked a lot about tools and data products. There was a lot of discussion on cadences and light curve cadences and data products in general. We haven't talked too much, I think, about pointing a little bit at the start and also the GI program. So anyone who has comments on those, please feel free to voice them. Diana had her hand up first.
Hi, Diana Dragomir, UNM. Any microlensing experts in the audience right now? Can you raise your hand, please? I want someone to check what I'm going to say. Otherwise, it's going to sound crazy. Okay. That's not a good sign. So one crazy thing I thought of yesterday was, could TESS overlap with Roman in time and space, even if it's just for a sector? Of course, depends on when Roman launches. And the idea would be if the two missions, I think they are separated enough in space, you could do, you could calculate the microlensing parallax and help break degeneracies in, what is it, like mass, microlensing mass, velocity, distance degeneracy, and basically get the planet, microlensing planet mass determined accurately, right? And you don't have that degeneracy anymore. So if that's a way, if that's something to think about maybe towards the end of EM3, I just want to put it in people's minds if it is feasible, because maybe it's just a matter of timing. And then Roman would obviously find the event first, right? And then TESS, we know where to look. So even though the pixels are large and there's a lot of blending, you know where to look. So you know, you have the Roman side that's going to give you the sub-properties, and then using the different shape of the microlensing event, you can maybe break the parallax and do that for a number of systems.
I don't know if Tom Buckley's here, but I see Mark has his hand raised, and he will talk about TESS and Roman later. So
yes, I'll actually be talking about some astroseismology related to TESS and Roman tomorrow. But in terms of the planet microlensing, I think the challenge is that the bulge fields are quite crowded, and most of the microlensing sources are typically quite faint. There could be interesting synergies between TESS and Roman in the high latitude time domain survey mission, which is more of a supernova or transient search. And I think that, and there is actually, it might actually be interesting, but if there was anything that TESS picked out in the Roman bulge fields, it would likely just be the most luminous stars.
Okay, we probably have time for one more. So I encourage again, anything related to pointing, so the GI program, which we haven't focused on too much. So yeah, in the back.
Hi, I'm Ben Cassese. I'm a graduate student at Columbia. I just wanted to point out, reflecting on the different pointing options that we saw in Roland's talk, the majority of all the solar system observations that we get right now are just on the very lowest CCDs of the very lowest camera at the very bottom of the CCD. So obviously solar system is not a priority for TESS, nor should it be. It wasn't the design, but any shift away from the ecliptic will probably completely cut off new solar system observations.
Yeah, very good point. We haven't heard much from the solar system community, so it's good to hear, for sure. Yeah. All right, maybe one more. We have another minute. Yes.
Hi, so in response to that last question, I'll be talking about solar system observations at 11, and particularly about how the pointing and cadence of TESS affects solar system observations. So thank you, that is a great.
Yeah, it's a very timely topic, because the next session, I think, will be all about solar system science. Okay, so we're at the half hour, so we'll wrap it up here. Thank you all so much for participating to this. This will not be the last time that you can provide feedback to both the TESS project and the TESS Users Committee. So we're around. Hopefully you've seen us all now. If you want to continue the conversations, we're around this week. But keep in mind, if you have any specific ideas and suggestions for the extended mission planning, as Allison said, this will be ramping up pretty quickly. So don't wait too long with your feedback, but you can always, of course, approach us. So let's thank everybody, all the speakers, and thank you all for participating.
Hello, everyone. Thanks for having me today. I'm Deb Woods, and I'll be talking about contributions of TESS to solar system science. I assume the mic is all right. You can hear me? Cool. Great. How do I advance? this one? Thank you. Alrighty. So just to put this in context, solar system objects, when I talk about solar system science with TESS, well, what targets, what objects are we talking about here? So in the inner solar system, of course, there are asteroids, including main belt, near-Earth objects, Trojan asteroids, which you'll hear more about in one of the next presentations. Also comets, inner planets, planetary moons, and diffuse matter. And then the images just represent locations of these objects. The image on the left is the view from above the ecliptic plane, and the image on the right is the view from across the ecliptic plane. So of course, one thing you'll note here is that in the inner solar system, most of the objects, most of the matter is concentrated in or near the ecliptic plane. Zooming out to the outer solar system, on the left is the view above the ecliptic plane, on the right is the view, excuse me, on the left is from above, on the right is from across the ecliptic plane. And while the planets are still mainly in the ecliptic plane, there's a lot more objects that are coming in at larger ecliptic latitudes, including mainly, as you'll see in these little white arrows, those are representing comets, as well as there are asteroids still out there, Kuiper belt objects you'll hear more about as well today. There are planetary moons. Further out, we have the Oort cloud and diffuse matter. So again, just for the context, we're talking about what is TESS's potential contribution to solar system science. Well, here's some of the things that TESS may be looking at. So an outline for my talk. I'm going to discuss TESS attributes and applications to solar system measurements, science that's being done with TESS, and just a little bit to keep in mind about having these solar system objects in your field of view. So the animation on the left, as you're all very familiar with, is showing the TESS cadence, stepping through each of the years. And things to note, as you know, everyone in this room is probably very familiar with, the sky coverage, it persists for 27 days per sector. The pointing is centered at opposition, so opposite the sun, which is done, of course, to keep good thermal stability for the TESS spacecraft for very good photometric precision. But this is also helpful when you're looking at, for example, asteroids, because opposition is like full moon. So they're brighter. The regions, as of course the coverage, as you know, in years 1 and 3 looks in the south, years 2 and 4 looks in the north. The ecliptic plane is included during years 4 and 6. And I was really interested to hear the discussion this morning about potential pointing strategies in future years. And as was an excellent question that was asked about how this will affect our solar system science, as you'll see, of course, this is going to be really critical for what future solar system science will be coming from the TESS data. So these graphics are just to represent where are objects in the solar system relative to where TESS is looking. So the panels on the top are a view from a little bit above, and the panels on the bottom are the view from across the ecliptic plane. I took the positions of all 1.3 million asteroids in the Minor Planet Center catalog at one time, plotted their position relative to where the projected fields of view of TESS. A couple things to note, there's the also plotted here for position is the sun with a red circle and the Earth with a blue circle. Their positions are accurate, their diameters are not to scale, or the Earth wouldn't be seen at all here. The asteroids are, of course, orbiting the sun, and so that yellow mass of matter is concentrated around the sun, whereas just for the sake of the projection plots, the TESS fields of view are centered around TESS, which is closer to Earth. So that's why you see a little bit of an offset of where's the projected field of view relative to the asteroid belt. So again, just for context, looking at year 4 in particular, where you see fields across the ecliptic, you're going to have a lot more objects in the solar system in your field of view there, of course. So again, this is just the accumulation of years 1 to 5, where is TESS looking relative to where are these solar system objects. So it's interesting to hear about potentially even filling in that gap that's shown in future years. So when thinking about the TESS mission and how its design relates to solar system science, because of course TESS was designed as an exoplanet survey, and it is doing an amazing job at exoplanet survey and an amazing amount of other science. I really enjoyed hearing about some of the range of science returns that have come from the TESS mission. But when thinking about it specifically for solar system observations, things that are important for what kind of science in the solar system you're getting are, of course, the sky coverage and cadence, In particular, in the Southern Hemisphere years, that coverage is really helpful because most of the major time domain surveys that have been operating, for example, Pan-STARRS, Catalina, Zwicky, those are Northern Hemisphere surveys. When Vera Rubin comes online, that's going to be a really interesting opportunity for more Southern Hemisphere coverage. But for now, TESS has been unique in its coverage all the way to the southern poles. Opposition pointing means that, for example, asteroids are fully illuminated. It's like full moon for an asteroid with the sun at your back. The persistence in pointing, and it's been interesting to hear the discussions this morning about, of course, it's the duration of a sector and what other science can be gained with that selection. It's been helpful for solar system work for long duration observations of time series objects. And of course, the pointing stability is really helpful because, as we'll see in the next couple slides, you're going to have to find these solar system objects sort of amongst your stars, and the pointing stability is helpful, as we'll see. The TESS camera, as you know, very wide field of view, so lots of opportunity. Depending on where you're looking, you'll have different amounts of different opportunities for things to be in your field of view. The TESS camera has very low noise CCDs, so this is great for sensitivity to faint objects. For the TESS mission, of course, it is super beneficial for really reducing the photometric errors and enabling detection of very small transit signals. Low noise is also extremely important for looking at faint things, so this is fantastic. The large pixels, though, do mean that you have a lot of sky in each location, and so this does limit the resolution and the astrometric accuracy. So when thinking about detections of solar system objects, solar system objects are pretty much by definition moving objects. The relative motion between the TESS camera and the object is going potentially to be substantial, either because the object itself is moving or is very close to TESS and is moving, or even for the more distant objects, there is parallax in relative motion because of the motion of the TESS spacecraft. So one thing that's different when thinking about solar system science compared to some of the other science that is being worked on is that moving object detection is pretty much a necessary prerequisite for doing solar system science. TESS data is mostly well suited to moving object detection. As I said, it's got low noise, it's got stable pointing, and this comes into play looking at these images. So this is just a zoomed in cutout region of a single CCD, single frame. The image on the left is the initial image, full of stars and galaxies. The middle image is background subtracted, where I subtracted just a median, I think of about 18 frames. And you can see some residual artifacts from stars. And that is not anything to do with the pointing stability. That's a result of differential velocity aberration because of the relativistic motion of the TESS optics relative to incoming light and the TESS spacecraft. You end up with the stars apparently shifting on the field of view on the focal plane. And on average, this is corrected for in the TESS fields, but because it's differential and it's a function of the field angle and location, it is not corrected everywhere all the time perfectly. It's impossible. And so you end up with some artifacts. So it's important to remove those when looking for the sources behind them. So some of the attributes I mentioned that are very helpful, of course, the low noise, the stable pointing. It is challenging though with large pixels because you have a lot of overlap with background sources and your astrometric accuracy is limited. But there is phenomenal potential detection in these frames. So a couple different ways of thinking about it. There is single frame detection. So that is looking for objects that are bright enough to be detected in a single frame. So once static sources have been removed and the object image conditioning is applied, object detection is apparent as shown on the figure on the right. And this is appropriate for objects that are moving by more than about a pixel within a set of frames. And the set of frames is how you define your static image. Is it static over 5 frames, 50 frames? That will set the sort of rate of motion of things that you can find. And that length is sort of balanced by any changing conditions in your image, whether it is differential velocity aberration or stray light. If you are looking for very, very faint objects, it's necessary to consider multi-frame integration techniques, frame stacking. This has a different set of processing requirements, and this is appropriate for slower moving objects. Particularly, I know there's research being done for Kuiper Belt, and we'll probably hear about that later as well. So this is just some examples of what the images look like after one is applied this image conditioning with the static frame subtraction and image conditioning. These are just examples of cometary activity. These frames are taken from the Lincoln Near Earth Asteroid Linear Program that's been looking for asteroids in the TESS data. I particularly like the one on the bottom right. It's not showing up quite as well on this screen, but there's actually 2 tails on that comet. And one can see variation in the cometary activity over time. So this is just to show some examples of the kinds of things that are hiding in your TESS data. So TESS data has lots of possibility, right, for detection of things in the solar system. And there's a lot of good science being done with it. So I love this gallery. I took snapshots of all of the publications that I could find that have TESS data and application to solar system. So this is everything, including the data that was collected, since post-launch. 2024, there were 2 publications. 2023 had several. It's been active, considering that TESS was never designed for a solar system mission. So this is my attempt to be as inclusive as possible. If I missed anything, please send me a note later. I'd love to include it. But then thinking about these publications in terms of TESS's potential for solar system science, I wanted to look at some of the themes of the publications. And so looking at what each of these paper topics were, I grouped them according to theme. And as you'll see, the biggest one on the left is the categories of asteroid photometry, light curves, and rotational properties. So this is not very surprising considering TESS is a time domain survey. It's designed for light curves of exoplanets, and of course the regular cadence and the collection of this data has a lot of potential for solar system objects as well. But also there's interesting work being done on the measurement of cometary activity. TESS data is also a really great resource for algorithm development purposes. The availability of the data and a lot of the tools associated with it have really helped make it accessible and make it be a resource for these algorithms. There's also an interesting work looking at characterizing asteroid interference in the mission data. We'll see a little bit more about that in a moment. So I wish I could show highlights from all of these publications. In the interest of time, I just picked a couple. So this was a publication by Andras Paul in 2020, in which he analyzed the asteroid light curves and found 9,900 objects with rotational light curves that are well described, which tripled the number of solar system bodies with measured rotational characteristics. So from his paper, the plot on the left with the black line is this sample showing the distribution of rotational frequency for the measured asteroids. Other samples are shown in the red and blue. And then on the right is just an example of the data that contributed to that. The top line is the top row is the brightness versus time in the original data, and then the bottom row is basically the phased light curve of the asteroid. And from that, the rotational properties are fit. And then building on that, there was a recent publication by Sabo et al. And this is taking as input that catalog of 9,900 objects and looking at characterizing the rotation rates and light curve amplitude and how that relates to asteroid families. So asteroid families are defined as basically groups of asteroids with similar orbital elements. So in the top plot on the left, there's the eccentricity versus semi-major axis. In the bottom plot, there's inclination versus semi-major axis. And where these asteroids have similar orbital properties and are physically similar in location, they are associated basically in a family. And this research is looking at how families of asteroids properties differ from other families. So for example, the asteroids associated with being chronologically older tend to contain lower amplitude light curves, which suggests maybe they are more round. And faster spinning asteroids tend to be more spherical. So these are some interesting things to come out of this sample. This is just a highlight of TESS data used for the discovery of a potentially hazardous asteroid. Potentially hazardous asteroids are a subset of near-Earth objects in which the asteroid orbit intersects within 0.05 AU of the Earth's orbit and also are larger than 140 meters. So this was from data collected in May and June of 2021. The asteroid is shown there hiding in the frame. And again, this was pulled out of the data set that originally just looked like a sea of stars. And then in the bottom right is a graphic showing the orbit of this asteroid with the Earth, Mars, and Jupiter for reference. So the research I've talked about so far is using, is looking at objects in the inner solar system. Next, I'd like to zoom out to look at the outer solar system. So specifically Kuiper belt objects. So the Kuiper belt is composed primarily of icy objects, dwarf planets, dust, and comets. It has, at this point, more than 2,000 have been measured, but it's expected this is actually only a small fraction of what is out there. They're hard to find. They are distant and they are faint. And so the light we're seeing from them is reflected from the sun from very, very far away. So they are difficult to find, and it takes a lot of data collection and a lot of processing techniques to pull these out of the data. So stay tuned for more discussion on that. But Kuiper belt objects are interesting to find because the structure and the composition of the Kuiper belt helps inform solar system models. And so it's of interest, I would think, both for people studying solar system objects, but also for people studying exoplanet formation. So this is just a little bit about detection techniques. This is from the paper, it's more about techniques than, say, particular objects. So this is an example of a multi-frame integration technique shown on this plot. Each circle represents an individual object that was observed in the TESS data, shown on a plot by the object's orbital parameters. And this is showing, as frames are stacked, shifted and stacked, how the signal is built up. So it took over 1,000 frames of stacking to get to an SNR of 8.5 for this one individual object. And this is a moving object. So you're not just taking your TESS frames and just summing all of them, right? You have to, in a computationally efficient way, shift and stack the images in a way that pulls out these potential detections. So lots of interesting things in the TESS data. I'm going to talk a little bit also about what to be thinking about when analyzing TESS data, even if you're not intending to be studying solar system objects. So this is another way of looking at the spatial distribution of asteroids in our solar system. On the left is a plot of their location in the sky in ecliptic latitude and longitude. And this is all the asteroids in the catalog at one point in time. As you can see, of course, most of the objects are located in the ecliptic plane. But as shown on the right, looking at the distribution of number of objects as a function of ecliptic latitude, certainly not all of them are in the ecliptic plane. It's not even down to 0 all the way close to the poles. And so just something to keep in mind, and this is really helpful and interesting for that discussion earlier about where should TESS be looking in future extended missions. If your goal is solar system objects, well, clearly you will get more if you're looking near the ecliptic plane, where more of the objects are located. But one should also keep in mind, you're trying to, for the science is happening on more distant objects, say distant stars, you're going to have to look through our solar system to see those objects. And so this interesting paper from Sorbella et al. Is showing how asteroid crossing events, this is where an asteroid passes through the aperture of a target star, can actually appear as a self-lensing event. So this paper showed how you can actually get a consistent fit to your model of a self-lensing event, specifically between a high mass compact object eclipsing a stellar mass companion in specific conditions in which your model fit is completely consistent with a self-lensing event, but actually what happened was an asteroid passed by. So it is worth keeping in mind. Again, solar system objects are really interesting in their own right. Also be aware of them even if you weren't planning to think about them. This is just another example of asteroids interfering in your TESS targets. So the top line is showing examples from TESS catalog stars where there are 12th magnitudes of very bright object passing within 5.5 pixels, and you get an apparent flare, right? Because you now have flux from your asteroid within your aperture. But a little more insidious in the middle row, this is cases where you have an asteroid that passed within the background aperture. And so if you're automatically detecting your background and then you have an asteroid there, you're going to over subtract your background, leaving an apparent transit behind. So these were not transits, these were asteroids. And these are not uncommon. The bottom row shows some examples where you have more than one asteroid crossing event in a single star in a single sector. So just things to keep in mind as you're studying things that are not solar system science. But TESS data has got a lot of useful properties for solar system. Its stability and low noise and persistence are really phenomenal for collecting data, particularly for time domain analysis. It's also produced a lot of great data for algorithm and methodology development. And so there's a lot of great science that's coming out of this. So stay tuned for a couple examples of the science that we'll see. Nora Takacs will be talking about exploring physical properties of Jupiter Trojans and Hildas with TESS Space Telescope. And then Cassese will be talking about initial results of a TESS Outer Solar System Survey. Thank you.
Thank you for this talk. Aviv from the Weizmann Institute. Is the fact that the TESS mission preferentially observes the high ecliptic latitudes is good or bad for you? Because these are usually less covered by asteroid surveys, as far as I get it.
So it is helpful to have coverage where other surveys are not looking. Yes, so there are some unique opportunities for discovery at the very highest ecliptic latitudes that are not covered. There will be fewer than if you're looking, though, at lower ecliptic latitudes, of course.
Great talk, thank you. What are some other bulk properties of the asteroid belt that we can learn as TESS's baseline increases? Like, what does more data give us about these objects?
Yeah, I think one of the things that's going to be particularly valuable from TESS are these time series analysis. So having larger samples of rotational properties, for example, I think will be very helpful. Increasing the sample, looking for trends, looking for families, and particularly time series. I think also cometary activity will be interesting, again, because of the persistence in the time series, so that one can look at actual changes in the cometary tails and flares and things that happen that would not be captured by, there's a lot of surveys that are doing asteroid discovery, but they don't stare for long enough to see these kinds of changes. So that's one thing that's unique to TESS.
Maybe you can elaborate, what do we learn from rotational light curves of asteroids?
I might ask Andras to, if he wants to respond about that one.
So I think that one of the most interesting findings of this surveying, that most of the knowledge of ours related to asteroid rotation is coming from ground-based surveys, which means that there is a sharp cutoff of the known rotation periods slower than 6, 7, 8 hours. So we don't really know what's the frequency, what's the proper distribution, and henceforth what's the history of solar system in this sense in terms of slow rotators. So I think that's the most important thing, because with TESS we can push this limit up to something like 20 days instead of something like 6, 7, 8 hours. So there is a huge difference. It's almost 2 orders of magnitude in terms of this type of knowledge. And there are a lot of solar system objects, small objects, which rotate just very slowly.
Yeah.
So it's highly unbiased in that sense. So that's the most important, but I would like to emphasize.
And to build on that, I think this cataloging of objects at different rotational properties helps inform the history of the solar system, right? And how they formed, particularly for the asteroids, and what kind of collisional processes have been happening.
All right. In the interest of time, I think we should wrap up and go on. If you have additional questions for Deb, I just want to mention you can throw them in the Slack channel. There's a solar system channel available, and we'll give one last round of applause for Deb. Our next speaker of this session will be Nora Takacs from Conclia Observatory, speaking about exploring the physical properties of Jupiter Trojans and Hildas with the TESS Space Telescope.
Yeah, so hello everyone. I'm Nora from the Conclia Observatory from Hungary. And can I get my slides, please? Well, until then, I know that most of you are used to venturing far beyond our solar system, exploring exoplanets and variable stars. But for now, let's take a little detour into our own cosmic backyard. Coffee break, somebody? Well, I could do my presentations, but I have cool images, so. So, yeah. TESS is known for its mission to discover exoplanets and study variable stars. However, it is also invaluable within our own solar system. By continuously monitoring large areas of the sky, the Space Telescope has collected extensive amounts of data on asteroids and providing insights into their orbits and behaviors. For example, TESS observed, as it was mentioned, around 10,000 light curves from main-belt asteroids during its first year only, which is 3 times more than ever observed before from the ground. In our research, we use TESS data for Jupiter Trojans and Hilda asteroids. Trojans are a large group of asteroids sharing Jupiter's orbit. They are at a distance of 5 to 5.3 astronomical units from the Sun in 2 main groups known as the Greek camp and the Trojan camp. They are located at the L4 and L5 Lagrangian points of Jupiter, and more precisely, they are at the Greek camp is in the L4 Lagrangian point, therefore ahead of Jupiter, and the Trojan camp is in the L5, trailing behind Jupiter in their orbits. They are believed to have formed in the outer solar system and then later being captured during the giant planet instability era. Hildas are located at the 3.42 to 4.53 astronomical units from the Sun in a 3 to 2 orbital resonance with Jupiter. They show a triangular distribution in their orbits so that they meet closest to Jupiter's orbit in the L3, L4, and the L5 Lagrangian points. And they are also likely have formed in the outer solar system and then later captured into this resonance with Jupiter, probably along with some inner solar system objects. Asteroids can be categorized into taxonomical classes based on their spectral behavior. Hilda and Jupiter Trojans are primarily classified as P and D types. These 2 types describe a surface as dark and red, therefore making the Trojan and Hildas the darkest and reddest objects in our solar system. These 2 can be further divided into red and the less red subclasses, and in our research we also investigate the differences between these 2 subclasses. Despite their large numbers, the rotational characteristics are only known for a relatively limited sample from ground-based measurements. The rotational period and amplitude distributions from the ground-based measurements are strongly affected by ground-based biases, as it was shown in recent studies using data from the K2 mission. But both Trojan and Hilda asteroids are important because they are the touchstones for solar system evolution models. And moreover, Trojans are also time capsules from the earliest days of our solar system, dating back for more than 4 billion years ago. And this is where we can mention the Lucy space mission, which will encounter 4 Jupiter Trojans during its way. And whatever Lucy finds will give us vital clues about the formation of our solar system. Our main goal was to determine rotational periods for as many Trojan and Hilda asteroids as possible using TESS data. We obtained TESS measurements for 439 Trojans and 513 Hilda asteroids. We were able to determine rotational periods for 406 and 444 objects respectively. We are working with a significantly larger sample compared to the reliable 102 and 96 objects from the K2 mission. We examined the light curve amplitudes in the function of the observed and absolute brightnesses. Here you can see here the colors represent the different signal to noise ratio intervals, and the empty circles are the upper limits for the objects where we couldn't determine any rotational period. The detected light curve amplitudes show the expected fairly strong correlation with both the observed and the absolute magnitudes, which describes that if an asteroid is fainter, then we can only detect larger amplitudes. On the following cumulative distributions, we compared results from different databases. The top two ones are for the periods, and the bottom ones are for the amplitudes. In the case of the period comparison for the Jupiter Trojans, so the upper left image, there is a similarity between the test results, the red line, and the results extracted from the K2 mission, the orange line. And another important thing to highlight is when comparing the test results, again the red line, with the green main belt asteroids, you can see that there are fewer short periods and more larger periods than in the main belt. This trend can also be seen in the blue line, the light curve database set. And this can be described due to the fact that the density of the Trojans is low. Therefore, if they are rotating faster, they will break apart. And this results to us that we will have less fast rotators. Moreover, when looking at the light curve database set, again the blue line, this mostly contains results from ground-based measurements, and due to the duration of the measurements during a single night, the top of the curve flattens out, and there will be no large periods observed. But in the test results, we can still find some slow rotators. The same similarities can be seen in the case of the Hildas too, but less drastically. Here on the top two figures, you can see the amplitude in the function of the frequencies. And on the right-hand side is the figure from the fossil survey. You can see that they have found a single Hilda asteroid that is a fast rotator. It rotates faster than the other Hildas or most of the main belt objects. But this can be described better with the lower figure. Here you can see how the frequency is related to the absolute brightness, which can be associated with the size. On a side note, we know that most of the asteroids are made up of rubber pies. We know this because through history, we have already visited some with space probes, like for example, Ryugu, Bennu, Itokawa. And for main belt objects, there is a defined limit for how fast they can rotate. And if the rotational frequency is higher than this limit, they would break apart. And this is why we cannot see a significant number of main belt asteroids above this line. And furthermore, we can assume that Trojan and Hilda asteroids have lower densities than the main belt asteroids. Therefore, this spin barrier would be lower for them. And you can see that on the image itself, that the majority of the Jupiter, Trojan, and Hilda asteroids are way below than the spin barrier for the main belt asteroids. And we can come back to the important part where the yellow dot above the spin barrier on the left represents the single fast rotating Hilda from the fossil survey. And we have found 4 additional fast rotating Hildas from the test samples. And they are also larger in size. Oh, and the gray cloud on the top left of the figure are the near-Earth asteroids that are small. Therefore, they are not made up of rubber pies, but more like a monolithic. Therefore, a massive rock that cannot fall apart due to fast rotation. Here you can see the spectra and the light curves for the 4 TESS fast rotating Hilda and the single one from the fossil sky survey. You can see that the TESS provided us more finer and better detailed results for all cases compared to the fossil survey one. These results are based on TESS data for up to sector 55, and the survey of sector 81 is currently in process, so we will have even more data in the future. And in the case of the main belt asteroids, sector 15 to 55 has not been processed yet, so we will have hundreds of thousands of light curves available. And if we since have so many light curve data for asteroids, it is possible to carry out even shape modeling on them. And for more information about shape modeling, you can check out my past poster in the poster section. And thank you for the attention.
Hi, Ben Shapi, University of Hawaii. My question is do you mind to give us the highlights of what the shape modeling with TESS looks like, what the results are, and how that compares to like ground-based shape modeling of asteroids?
Sorry, can you repeat that?
Sorry, I want to give you the opportunity to tell us the highlights of what the shape modeling of the asteroids with TESS light curves, what that actually looks like, and specifically how that compares to ground-based, shape modeling based on ground-based light curves.
Yeah, briefly said, the shape modeling is based on the light curve inversion method, where we need measurements from multiple directions that are relatively far from each other. And the amplitudes on those light curves will be different, and with those amplitudes, we can get a relatively simple shape modeling, where we assume that the asteroid's shape is with a triaxial ellipsoid. But I can tell you more about it during the poster session.
Time for maybe one more question, if there is one.
A quick one, Luke Bouma from Caltech. Is there anything new that we can learn about the abundance of sort of Arakoth analogs, so contact binary asteroids, maybe following up a little bit on the shape question? In other words, does that differ between these different populations?
I will be honest, I don't know, I haven't looked up into that, but I know people that do things like that.
All right, so let's thank our speaker one more time. And our last talk of this session will be by Ben Cassese from Columbia University, who will be speaking about initial results of a TESS outer solar system survey. I think he's getting his mic.
He wanted me to do the clip on. Mic transition.
All right, sorry for that. Yeah, so my name is Ben Cassese. I'm a fourth-year graduate student at Columbia. I mostly work on exoplanets, but while I'm here, I'm going to be telling you about the solar system, the project that I've been doing with Milena Rice here. So thanks to the organizer for giving me the opportunity to speak. Also thanks to the previous people for kind of laying out the geometry of the solar system for me to try to ground this in terms of an exoplanet audience. So I just want to put out to scale a diagram of the solar system that we have here. It went a little bit faster than I anticipated, but the point that I want to make is that everything that we've talked about for transiting exoplanets happen in this inner little dot there. The rocky planets themselves would be considered very, very long period transiting planets, but I'm going to be talking about things that take hundreds of years to go around their central star. So a complex dynamical structure, but unlike the type of things that we usually think about when we do transiting exoplanets. To further kind of connect the outer solar system to the exoplanet community, I also want to step through just the history of discovery of it very briefly. If you'll bear with me, this is, I went ahead again. Oh well. I want to emphasize that the outer solar system filled up very quickly. Our knowledge of it filled up very quickly on about the same time scale as our knowledge of transiting exoplanets. The very first TNO, or trans-Neptunian object, was discovered in the early 1990s. And if we look at the discoveries, I think I'm going every other slide. I think that's what's happening. So I'm sorry for this. Yeah. Yeah, I'm not sure what's happening there. I'm sorry. There should be a plot in the middle there. But I'll roll with it. So if we look, yeah, it's going every other slide. That's so strange. That might cause problems later, but we'll see what we can do. I'll put the outer solar system in context of TESS. So this is a beautiful mosaic from NASA Goddard that I forgot to put the citation on. And if we look at where the outer solar system objects would map onto this space, we can see that, yeah, it's every other, I'm sorry again. They're supposed to be a little smoother. But you can see that this is a randomly sampled selection of TNO orbits, and most of them fall right in the gap where TESS is not looking for most of their time. So if you want to find a TNO, you really need to look at just this bottom row of CCDs where you'd find the majority of the objects, even though they're kind of puffy in the outer solar system that we saw from Dr. Woods, that it does puff up a little bit. They're still all very well confined to that inner plane. All right. Yeah, we're really going here. That was a effectively random TNO. It's 620088. There's really nothing special about it. It's out about 50 AU, semi-major axis, a 300 and something year period. And if we zoom in, we can see that it fell onto a chip. And if we look at that chip here in sector 62, we'll go in pixel coordinates, what the motion of this object would have looked like. So if TESS were sitting in the center of the sun, yeah, it's every other slide again, sorry, it would have been a nice straight line. We'd have other problems with TESS in the center of the sun, but that's what the motion would have looked like, because just smoothly going around in a Keplerian orbit. But because TESS and the Earth are orbiting the sun, we instead get this much more complicated parallax-dominated pattern as it goes around. If you're thinking maybe TESS's orbit around the Earth complicates it further, it actually doesn't really. It would be a few arc seconds offset. So if it was a ground-based telescope or a high precision telescope, we'd have to factor that in as well, but it all falls in the same TESS pixel. And so the thing to note here is that this parallactic motion dominates the actual orbital motion. The object is effectively fixed in place over the course of a single TESS sector, and the Earth just kind of whizzes past it. So this is over the entire duration from TESS launch to today. So this is 6 years, 6 loops of it. And you can see the loops actually change size a little bit and offset a little bit as the object comes closer and further, is coming closer in towards the Earth. If we look to where this moves now, I'm sorry, that little bit was actually all of the motion that we would have seen during sector 62. It's just that little, like right there. And the length of it is set by pretty much its distance to us, instantaneous at that time. And it's very linear because it's just parallax. So we can, if you give me a distance from the Earth, I can tell you pretty accurately how that object will move on the TESS CCD because it's effectively fixed in place, which means there's only so many paths an object could be traveling on in the outer solar system. We skip that whole, okay. Here is how we might find that object. So what I didn't mention until now, and I was going to mention, is that that one that I pulled out is at a magnitude of 22.7. So well below the single frame detection limit in any given TESS frame. So what we need to do is do a shift stack or a digital tracking technique to try to actually boost the signal out of the stack of FFIs instead of any given one. So what that looks like in practice is we take a stack of images like that, and we put them, they collapse down onto one frame. So you have to pick the trajectory ahead of time that you want to stack. How far do you want to shift them before you collapse the stack? But again, if you're only moving about 150 pixels, if you want to search every possible path between 10 and 150 pixels, you're left with only a couple hundred paths to actually check. And also it's a highly scalable process. It's just addition and you can work in very parallel chunks. You can cut up an FFI into a bunch of smaller things and run them all in parallel on your compute cluster. So it's actually not infeasible to do a search like this based entirely on shift stack. This was not our idea. It's a technique with a long heritage in the search of the outer solar system. So it's been done in ground-based searches. It's been done in TESS a couple of times, including one by Malena. But we're trying to take this technique and do a blind search looking for other objects in the outer solar system. So here is that cutout. I think that trying to remember what was on the slide that got skipped. Man, yeah. Right. So in order to do that shift stack, you need to assume that everything has already been subtracted out, that your image is nothing but essentially white noise plus a little perturbation caused by your object. So you need to reduce all of the data before you actually do that shift. And so this is where what everyone else likes, stars and other things like that, become pure noise for us. So we actually just don't even bother with the stars and just completely subtract them out, just mask them entirely. The Poisson noise, the shot noise you get from a given star is significantly bigger than the background noise and significantly brighter than the signal itself. So even if you want to model the star, just the inherent uncertainty in the stellar flux will overwhelm your signal. You then do whatever you want to flatten the curve. I think that was surprising to me in this project is just how robust the TESS is so stable. No matter how you actually detrend each pixel, it usually works out. So we got pretty good detections out of just fitting a polynomial to every time series and subtracting it out. Got a little bit better by using a Gaussian process, a little bit better by doing like a PCA, but pretty much anything that will take a wiggly line and make it mostly flat, other than the small perturbations within the noise, will get you a good detection. So here is that object that I showed you. So this is an output of our like automatically generated report from our pipeline that we made. So this is again object 620088. You can see that in the animated version of the shift stack, this is the real version of the data. So it shows up as one bright pixel in an otherwise kind of sea of noise that you get when you stack together a bunch of random noise. You can see that as we sum pixels, the flux increases very linearly, as you'd expect, because we're centered always on the object. If it was just random noise, you'd expect this to follow a random walk. So you can see the final distribution is about 0.2, so it would be kind of like a little curve down here. So the fact that that is not a random walk, obviously, is a good confidence that it's a real signal. The right column of figures here is actually the hardest part of this project, and that is taking this very faint object and trying to do astrometry on it. Because the object is moving, and if you want to find it in the future, you need to fit in orbit. But an individual test pixel is so large, and you don't really know where it is within that pixel, and you're summing them all together. That's a very difficult task. So you can see here, this is the constraint that you get on the semi-major axis over an entire test sector. So it could be anywhere from 37 to 42. The inclination is also pretty poorly constrained, like 10 to 22 degrees. But that's still good enough that this figure here is 1 year later. Where could it be? So the blue points are predictions of its possible location. The red X was its true location. And this red circle is roughly the footprint of DECCAM. So if you were using DECCAM, which is a telescope facility on NORLAB telescope, you would probably be able to recover this object with a single pointing. You have it well enough constrained that you could find it again after 1 year. That is not the case in many of the objects that we found. A lot of things that are close in, or if it's been more than a year, even though we could detect it, it's not with sufficient astrometric precision that you would be able to recover that object again in the future, unless you wanted multiple tiles of a large ground-based facility, which is usually, it wouldn't be worth it. So I'm hoping this one shows up because, yeah, now we're going, nope, never mind. The report that I showed there was a similar report, but there was no known object near it. There were many of these. There were about 600 of those, but that was a particularly good one, and I would have showed you how nice the line is and all of that. But the upshot of all that is we applied for and got DECCAM time to try to follow up on some of these objects to see if we could successfully recover them. And we did, and I promise we did, and that was a nice GIF of it. There it is, yeah. So this is a new trans-Neptunian object. So this was not previously known, and we think it's the first TESS outer solar system discovery. We think it, at least in the literature, not that we've published this either, so maybe someone else has done it already. But yeah, there's nothing entirely remarkable about this object. It's solidly in the Kuiper belt, mildly eccentric, slightly inclined, but it's just a kind of cool demonstration that TESS is capable of making these types of discoveries, things that it was not initially designed for. And also worth noting, a plot a while ago that got skipped is that we only have between 1,000 and 5,000, depending on how you make the cut, confirmed outer solar system objects. So we're comparable numbers to transiting exoplanets. So still we're in the regime where one particular object might actually be interesting and is worth pursuing picking up these individual objects. So where do we want to go from here? One idea would be to do a full archival survey. So just take the pipeline that we've written and apply it to every TESS image ever taken. And again, like I said, you wouldn't be able to recover most of the unknown objects, but maybe you could do some cool population statistics, injection recovery things. But honestly, that's probably not the best use of our time because of LSST, which is there. LSST is, never mind. The point is LSST is probably going to find everything that TESS could find. They've modified their survey strategy such that they've got a mini survey that's going to hit even the north ecliptic areas within 10 degrees of the ecliptic plane. So there's no reason to do a population level study with TESS. The bullet point that got skipped over was it still could be worth it to do a real-time pipeline of if you can manage to actually churn out these reports soon enough that someone could use a small ground-based telescope, that could still be worth looking into. And the option that is the most unlikely for me to actually do as a graduate student, but that I'm actually very excited about, is the potential for TESS to detect interstellar objects. So this is a simulation that I did of Borisov, one of the two interstellar objects. You can see the green tracks here are inner asteroids. The blue are Jupiter Trojans, and Borisov just came screaming in on this trajectory that looks nothing like anything else. But if you do an injection into the real TESS data, using the real TESS PRF, using the real magnitudes, changing with time, and then you stack along blindly these extreme angle trajectories, you recover it with something like 18 sigma. So if TESS happens to have been looking where Borisov came in when it came in, there's a chance TESS could have actually been the facility to discover it. So I think there's real potential there in it being a time domain solar system mission moving forward of looking for these rare objects that wouldn't be there otherwise. So with that, I'll leave up the summary, which did work happily. That yeah, TESS is capable of discovering, of recovering known trans-Neptune objects. We pulled out about 100 in our small pipeline. We've confirmed at least one. We have candidates of about 100. Good-looking ones, 600 not so good-looking ones. And then, yeah, TESS has the potential to discover rare objects moving forward. So, thank you.
Lots of questions.
And thank you for your patience with the slides. Sorry about that.
Ben, thank you for your patience with the slides. Well done. Can you kind of go over again how it is that you pick the pixels to stack? Because it would seem to me that there'd be just this incountably large number of potential stacks that you could make out of a large number of pixels. So,
Sure.
yeah,
So if you can analytically write down what the motion should be across the detector if you have an object. You can just effectively pretend the object isn't moving. It's just a fixed point in space. And you take the TESS trajectory and see where that object would appear to be moving at that time. So when you do that, there's only, if you do integer number pixel shifts, which is a key thing there, like we're not doing any interpolation, there's only 1,000 trajectories that you might want to search in any given stack of images.
there are so many orbital elements to keep track of. I think that's what I'm struggling with here.
Yeah, so that's what's fun is that
dimensional problem.
You don't even need to think about it in orbital element space. Just like put an object there and pretend it's not moving. So, a given object at 35 AU, 1 AU above the plane, it could be eccentric, it could be not eccentric, it could be anything, it could be an ISO. I just pretend it doesn't move and it will do the same apparent motion on the detector.
Great, thanks.
Eric Gaidos, University of Hawaii. The discovery of interstellar objects is, of course, would be fantastic with TESS. I think the issue is that there are many objects in our solar system or that enter the inner solar system that are on parabolic, near hyperbolic or objects. So do you have any sense, and those are just long period or Oort cloud comets, do you have any sense of how good the ephemeris you can get with TESS to discriminate between those?
I do not, but I assume it's good enough to alert ground-based people to go get better ones. And also, if we found something that was near parabolic or near hyperbolic, it's probably a comet and it's probably interesting, so it's still worth flagging.
Francis Wilkin from Union College. It would be very valuable to find TNOs in the trajectory of the New Horizons spacecraft. I don't know if that's at all possible. They may be too faint.
Yeah, so actually, I think literally this morning there was an archive paper on a Subaru hyperscreen cam search for possible new TNOs in the path of New Horizons. The faintest thing we recovered was the one I showed you, which is 22.7. At this point, New Horizons is looking at like 25th, 26th. Like we're not going to be capable of helping out New Horizons.
Hi, Aviv from the Weizmann Institute. It seems like your search is a single sector search. Do you plan on making a multi-sector search?
Yeah, that's correct. Yes, and maybe. We've only done the one sector. The biggest constraint we face is just data volume. I mean, in those reports, we're summing 10,000 FFIs together in different configurations. So it's just hard to computationally manage that much. And also, the assumption you make of the linearity kind of breaks down the longer your time span is. Yeah.
All right, I think we'll wrap up there. If anyone has any additional questions for anyone in the session, I encourage you to bring them to the Slack, and we'll give one last round of applause to all of our speakers.
Okay, so good afternoon, everyone. So let's start the 5th session about exoplanets. We're gonna have 5 presentations about various aspects of exoplanetary systems. And the first speaker of the session is Nicholas Saunders from IFA Hawaii.
All right, thanks so much. Hi, everyone. My name is Nick Saunders. I'm a final year grad student at the University of Hawaii, and I'll be on the postdoc job market this fall. And I'm really excited to talk to you about some of the work that I've been doing to better understand how planetary systems evolve along with our host stars. So thanks so much to the organizers for giving me a chance to share this, and let's dive in. So I just want to start this session with a quick refresher on star and planet evolution. And you're all very familiar with this from your Astronomy 101. You have your pre-main sequence, and along here somewhere, planets form. You sit for a few billion years in a pretty stable configuration. Somewhere along here, the planets are destroyed, or maybe they survive as the star blows off its outer envelope and becomes a white dwarf, right? So pretty simple picture. We've figured this out, and we can all head home. But the reality is there are still some big mysteries and open questions in this process, particularly in these kind of transitions between the pre-main sequence to the main sequence, and then as the host star evolves. Then finally, there's some big questions about whether planets can survive into the very final stages of stellar evolution. And part of the reason it's challenging to really see the full picture of planetary evolution clearly is that it's really hard to find planets around evolved stars. So if we take a single transit from a hot Jupiter from Kepler around a main sequence star, it looks like this, right? It's very easy to pick up by eye, very deep, high signal to noise transit. But if instead we take a similar sized planet on a similar orbit and put it around a subgiant, its single transit from Kepler looks something like this, right? So the obvious thing is that the depth is much smaller, the signal to noise is lower, but it's also important that the duration of the transit has increased as the stellar radius increases. And you have these other features in the noise from the stellar granulation from the evolved star that kind of mimic transit features. And so it's easy to kind of pick out a few different things here that look like dips, but the transit is this shape right in the middle here. But with TESS, the full sky has been opened up to search for planets around subgiants. So we have a much larger sample to identify these low signal to noise, difficult to find transits. And we've developed a pipeline called GIANTS, which is a full frame image photometry pipeline that's really designed specifically to find these long duration, low signal to noise transits. And so as you can see in this example, these transits that can last 8, 10, 12 hours are really easy to accidentally remove in your detrending algorithm. And so we have a focused effort to preserve these transits and find them in the TESS light curves. And I think this is a really good example of how a community collaborative search can be a really good way to find planets around the full range of stellar host stars. So if you want to learn more about this, please check out the posters by my collaborators, Sam Grunblatt and Emma Page, and the poster numbers are up there. And if we look at the picture of the population of planets orbiting evolved stars before TESS. This is what the transiting planet hosts look like. And you can see that it's really dominated by main sequence stars. There are a few things up around subgiants and up the red giant branch, but it's pretty sparse. And since TESS launched, we've been able to really fill in a lot of this space. And so this is, you can see the black points on this Kiel diagram show transiting hosts from TESS, and then planets identified, or the host stars of planets identified by our transiting giants survey are shown as the red stars. And so we have some of the most evolved transiting planet hosts, and we're learning a lot of really interesting things about how these systems change along with their host stars. And so during my thesis, I've been interested in a few questions in particular, which I'll highlight here. I really am hoping to understand better how and when hot Jupiters become inflated, how the orbits of these planets change, and ultimately how the occurrence rate of giant planets change as a function of stellar evolution. But today I'm going to be focusing on this middle question about how the orbits evolve and what we can learn from that. If we look at the popular ideas about how hot Jupiters form, for example, there are a couple that I've highlighted here, the idea of disk-driven migration, where a giant planet forms far out in a disk, then gradually loses some of its orbital angular momentum and moves into a close-in orbit where we observe it today. Or high eccentricity migration, where some dynamical event through gravitational interaction with a giant planetary companion or stellar mass companion scatters the Jovian planet into a highly eccentric, often misaligned orbit, and then it gradually circularizes and in-spirals into a closer in orbit. And if we want to be able to distinguish between these formation scenarios, it's really important to understand the processes and the timescales of these processes that govern the evolution of orbits. Specifically, these ideas of in-spiral, circularization, and realignment. And so by getting a better handle on how these things operate and over what timescales, we can start to get a better picture of how hot Jupiters form. Specifically, if we look at the predictions for each of these formation scenarios, disk-driven migration predicts circular and well-aligned orbits for planets orbiting or hot Jupiters orbiting all stars in the absence of any other kind of dynamical processes, while high eccentricity migration predicts circular and often misaligned orbits around hot stars, and circular and well-aligned orbits around cool stars, but only if there's some mechanism that can efficiently realign those hot Jupiters around cool stars. And if we look at the observations, you can see here the stellar obliquity on the y-axis against the effective temperature on the x-axis. And the stellar obliquity is just the angle between the stellar spin axis and the orbital plane of the planet. You can see these things that sit down at the bottom are well aligned, and most of the cool stars are predominantly aligned to the orbits of their planets. And the hot stars display this really broad range of obliquities. I'm sure you'll see this plot a lot in this session. But I've also just highlighted the kind of distinct distributions that these seem to follow on the far right. And so one thing that's very interesting to ask is if you have a star on the main sequence with a hot Jupiter that's on this end of the craft break and is hot and it's in this population that's typically misaligned, what happens as the host star evolves and crosses into the cooler region where the population is predominantly well aligned? And one of the reasons this is an interesting question to ask specifically for these subgiant stars is if you look at the interior structure of what's actually happening inside these stars, I'll show a very quick cartoon version of where convection is happening. So convection shown just by the little circular arrows. A solar mass star on the main sequence has a radiative core and a convective envelope. As it evolves, it cools and expands, but it maintains that same structure. A star that's more massive than the sun has the inverse structure. It has a convective core and a radiative envelope. But as it evolves, that structure flips. Its convective core quenches. It gains this deepening surface convective envelope and kind of mimics the structure of a lower mass star. So on the main sequence, this break happens around 6200 Kelvin, metallicity depending. But things that are more massive than about 1.2 solar masses will actually cross the craft break as they evolve. And if we want to measure the obliquity, that stellar obliquity that I was showing on the previous slide, we can use something called the Roster-McLaughlin effect. So this is done by taking radial velocity observations during a planet's transit. So as the host star is rotating, part's blue shifted, part is red shifted, and the planet crosses the limb of the star and blocks some of that light. And so a well-aligned system shows a nice symmetrical kind of S-shaped additional component in the radial velocities. And I just want to quickly highlight that this type of observation can be used to learn really interesting things about multi-planet systems and kind of reveal the architecture and histories. So if you're interested in seeing this applied, please check out Jingwen Zhang's poster and her paper that was posted to the archive this morning. Now looking at the stellar radii and effective temperatures of stars for which this observation has been made, I just want to highlight a couple things. So you can see that clear, distinct distribution on either end of the craft break. And the other thing I want to highlight is that this is really dominated by main sequence systems. There are very few evolved systems that have crossed the craft break for which this type of observation has been done. This is mostly because in this region it's very challenging to measure the Rossum-McLaughlin effect. All of the things that kind of contribute to a high amplitude Rossum-McLaughlin signal are diminished as the host star evolves, which I've highlighted here. But we were able to find a few systems that are in this kind of very important parameter space to understand this evolution, and we could also get this measurement for them. So I'll show those measurements now, no more suspense. Here is the very first one that we obtained. You can see that this hot Jupiter orbiting a subgiant that sits just on the cool end of the craft break is very well aligned and consistent with a low obliquity. The second one we obtained very low obliquity. And then finally, we obtained one with KPF recently, which again is consistent with a well-aligned system. So this is pretty interesting and kind of surprising because now we have things that were hotter than the craft break on the main sequence, part of this kind of broad distribution of obliquities, and now all sit right on the cool end of the craft break, consistent with this well-aligned population. And the question becomes, can you take a system that's misaligned around a hot star on the main sequence and efficiently move it down into this part of the stellar obliquity space? And so we modeled the damping of orbital period and obliquity for these systems. You can see in this plot age on the x-axis against the orbital period in the top panel and the stellar obliquity in the bottom panel. And I'll jump scare really quickly an equation, but don't pay too much attention to it. I just want to highlight a few things that change as the host star evolves. So the things highlighted in red change as the star swells up, its mean density changes, its radius changes, and then this orbital period also changes indirectly. And all of these things accelerate these damping timescales. So the things that are orbiting evolved stars are undergoing these tidal processes on much quicker timescales than things on the main sequence. And the problem here is that these stars enter a phase of runaway in-spiral, where their orbital period is decaying rapidly before they have a chance to align. And one potential solution, and so they'll be engulfed before they're able to fully align. And so one potential solution is that if there are different efficiencies for the damping of orbital period and obliquity, you can create a scenario where the planet survives without being fully engulfed and is able to realign. So there are a few theories for why this might happen. This isn't us just putting our thumb on the scale. I'll just show them here. Feel free to talk to me about them later. But one in particular, the idea that inertial waves can get driven through a convective envelope, seems to introduce a pretty consistent difference in these efficiencies to what we use in our models and seems to describe the pathway pretty well. And so we can drop this realignment track onto our stellar obliquity distribution and show that there is this pathway from a misaligned hot Jupiter on the main sequence to this well-aligned population that we're seeing. And this seems to support the idea that with the addition of this efficient realignment, high eccentricity migration is a valid pathway to form hot Jupiters that describes the kind of misaligned hot stars and the well-aligned cool stars. All right, with that, I'll leave my summary slide up. This is the paper here on this QR code. If you want to check it out, it just appeared on the archive today, and I'll take any questions. Thank you.
Thank you very much. I think we have time for one or maybe two very short questions.
Thanks, Linhao Ma from Princeton. So what can you say about the few systems with cool stellar hosts, but still high obliquity in your plot?
Yeah, so these things that are sitting up here.
Yeah.
Yeah, there's a couple ways that you could explain this. So one may be that these are recent arrivals, things that were scattered kind of later in their host star's evolution. They may be young systems. I'm not really doing any kind of filtering for age here. And there are also ideas that there are stable orbital configurations other than well-aligned for things with convective envelopes. So Seaman Albrecht has a paper called, it's one of my favorite paper titles, it's A Preponderance of Perpendicular Planets. And it's this idea that you can end up with perpendicular orbits that are stable. So it could be any of those.
Thank you.
Yeah.
Okay, so just one very short question.
Thanks. Since you're relying on inertial waves, you need the Coriolis force to be the dominant restoring force here. And so I wonder what kind of criteria you use in your theory in terms of frequency ratios between all acting forces.
Yeah, exactly. So it's the Coriolis force that's driving these inertial waves. And it makes sense that this would start driving the waves as the convective envelope reaches some threshold of depth, because you need some convecting material to drive the inertial waves in that misalignment. We have a very simple kind of toy model for that prescription. We basically just say, as soon as the convective envelope reaches this critical depth, then these inertial waves increase the efficiency. And I think with a finer sample of Roster-McLaughlin observations along kind of a tighter range of evolutionary states where we know well the convective envelope depth or can constrain better the convective envelope depth, then we'd be able to get at those ideas of what frequencies are efficient and things like that. But at this point, it's basically just saying, can this explain the trend we see?
Okay, thank you very much.
Right.
Thanks again. So the next speaker is Alexander Wenner from University of Southern Queensland.
Thank you very much. Okay, yeah, thank you everyone. I'm Alex. I'm a final year PhD student at the University of Southern Queensland in Australia. And I'm here today to tell you about my work with using astrometry to understand the long period companions in TESS planetary systems. Yeah. So, if you didn't already know it by now, transits tell us a lot about short period planets. However, once you go towards longer orbital periods, the transit probability becomes very small. So to learn about the outer regions of these exoplanet systems, we need to use other methods. Until now, most of what we already know is from RV follow-up. So this involves detecting transiting planets, then pointing spectrographs towards those same stars to look for the RV signals from long period planets. This has done a lot for the field, but there are some limitations I would like to point out. First, there is the practical cost of doing RV follow-up for these stars. Spectrographs don't come cheap. And observing stars for several months or years does have its operational costs. And second, astrophysically, RVs don't give us information on the mutual inclinations in systems. Why do we care about this? Well, we understand that planets form in disks, that they form from the protoplanetary disk that form around the star. So we understand that planetary systems should form with primordial alignment. They should have flat orbital planes. However, we have seen through the last decades of exoplanetology that we see all sorts of misalignments in exoplanet systems. Here we have the examples of Roster-McLaughlin misalignments in hot Jupiters, and also the beautiful example of the severely misaligned orbits of the long period planets in Upsilon Andromedae. So we want to know how you get to exoplanet systems to these states, which are quite dissimilar to what we see in the solar system and what we think they originally looked like. So our goal is to measure the mutual inclinations between the inner transiting planets and the outer planets in the same systems. And to do this, the only applicable detection method is astrometry. The best astrometric precision that's ever been attained is from the Gaia mission, which is an ESA space mission, which has been in space for about 10 years, measuring the positions of stars across the sky very precisely. Gaia astrometry will be sensitive to Jovian mass planets with orbital periods of around a few years, which is a very strong complement to missions like TESS, which are sensitive to planets with orbital periods down to the scale of days. However, as we all know, the epoch astrometry from the Gaia mission has yet to be published. The first release is expected for the Gaia Data Release 4, which will not be earlier than 2025. So we can't do this yet. What we have for now is Hipparcos Gaia astrometry. And what do I mean by this? So prior to the Gaia mission, ESA had an earlier space mission called Hipparcos, which measured the positions and proper motions of bright stars across the sky around the epoch of 1990. The currently available Gaia data gives us the same information, but around the epoch of 2016. We can combine the two by cross-calibration, putting them onto the same reference frame, which gives us the information of the proper motions of those same stars, separated by about 25 years. And by combining the positions which the two satellites measured, we can trivially convert that into the mean proper motion between the two sets of observations, the mean amount of proper motion that the star has undergone during the 25-year interval. The precision from this is sufficient to detect the accelerations from long period planets and more massive companions around most of the stars in the Hipparcos sample. So this might be a little difficult to intuit. So this here is a wonderful diagram from a recent review paper by Tim Brandt, who really has done a lot to pioneer the method. So over here, if you can see, this is the simulated epoch astrometry from Hipparcos. So Hipparcos was measuring the positions of the stars in RAN-DEC over time. And if there's an orbiting companion, it would measure the median proper motion across the span of observations, which would be facing this way. Gaia has revisited this star after 25 years. And the simulated companion has moved around on this orbit. So Gaia is observing the star moving down here. The Hipparcos Gaia proper motion, the mean proper motion I was talking about, is the displacement between the Hipparcos position and the Gaia position. And once we average over the 25-year interval, it gives us information on the long-term acceleration of the stars over the scale of decades. With only 3 measurements of the proper motion, the Hipparcos Gaia astrometry can't give us orbits by itself. So what I've mainly worked on is combining astrometry with archival long-term RVs. And I want to take a moment to acknowledge that this archival data didn't come for free. My work has been built on the backs of decades of work by hundreds or thousands of observers. So to explain what's going on the right here, we have the proper motions for Hipparcos and Gaia. This is in right ascension. And on the right-hand panel, I'm showing the mean motion. So if you can follow the model curves on this panel, what the mean motion shows is the integral under the curve. So it's the mean proper motion between these two epochs. So this is a particular planet which I've been working on recently around a sun-like star from the long-term RV surveys, which has a planet with an orbital period of about 25 years and about 6 Jupiter masses. So this gives you an indication of the scale, or the relatively small scale of the astrometric signal for these kinds of planets. If we're looking at combining this with test systems, we do run into a problem with the numbers, however. Here I'm plotting a histogram of the brightness of all the TOIs, the TESS host stars, for which there's about 5,500. So as you can see, this is very much skewed towards the right, towards fainter stars. If we do a cross-match with the Hipparcos sample, however, we have only about 5% of the sample, about 250 stars, which are matched with Hipparcos. And as you can see, these are mainly skewed towards the left. If we then consider stars which show a significant astrometric acceleration, we have only about 30 stars, and you can barely see it on these axes. I'll have to zoom in. So this is the distribution of stars with significant astrometric accelerations, which are also TOIs. So this is only about 0.5% of the whole TOI list. And unfortunately, most of these stars are in fact binaries, which is easy to understand if you think about how, if you can detect planets at this level of precision, if you have brown dwarfs or stars orbiting those same stars, they will cause a much larger astrometric acceleration. So with the existing astrometry, planet population statistics, like I was talking about, are not yet feasible. But we do have individual systems and they are informative. I'll start with the example of HAP-P2, which is one of the early hot Jupiters from the ground-based surveys, which has been redetected by TESS. Because it was detected so early, we have well over a decade of RV data, which I'm showing on the left here. What I did was combine it with the Hipparcos sky astrometry on the right. And as you might be able to see from these plots, the astrometric signal is consistent with a very low acceleration. What this does is allow us to solve for the order periods of the outer companion, and also gives us a constraint on the inclination. And for this, the outer planet HAP-P2c, I found that the inclination is very much consistent with 90 degrees. As the transiting planet also has an inclination of 90 degrees. This is consistent with general alignment in the system at the scale of 10 AU. But it's not always so simple. And the best example for this from the Hipparcos sky astrometry is definitely Pi Mensae. So Pi Mensae had a known planet from the RV surveys with an order period of about 6 years and a very high eccentricity. One of the first test discoveries was the inner sub-Neptune orbiting this very bright star. The Hipparcos Gaia astrometry is sensitive to the astrometric signal of the outer companion, and this has shown that the orbits of the two planets are significantly misaligned. What I'm showing here on the right is the projected orbit of the outer planet. As you can see by eye, it's significantly misaligned to our line of sight. And this means that there's a mutual inclination of at least 30 degrees between the inner and outer planetary companions. Combined with the high eccentricity of the outer planet, this seems like clear evidence, a smoking gun for scattering in the outer system, that there's been some sort of dynamical excitation of the outer planet. I wanted to highlight here also an interesting system which has been recently discovered by TESS. TESS has detected two very small planet candidates around this bright star, HD 50554. The star is also known to have a giant planet from RVs with an order period of about 3 years. The eccentricity is also about 0.5, which is quite high, like Pi Mensae b. So I want to see if a system is significantly misaligned as well. Here I'm plotting the RVs on the left and the astrometry on the right. And as you can see here, the model is quite fuzzy. This is because the astrometry is not doing so good of a job at constraining the inclination of the outer planet. The 3-year orbital period of the planet is quite short relative to the span of the Hipparcos sky astrometry, so the inclination is not very well constrained from the data. As you can see, the uncertainties are very large, and it spans from about 45 degrees to 130 degrees. And in this case, I think this will be better suited for solving with Gaia DR4, the epoch astrometry from Gaia. So as a quick conclusion, astrometry has a unique synergy with the transit method for understanding system architectures. It gives us information about the broad scale of planetary systems. We don't yet have the capacity or the capability to measure the planetary inclinations in large numbers. What Hipparcos Gaia astrometry has given us is really the best, the brightest of the available systems. Most systems are consistent with being aligned, like HAP-P2 as I was talking about, but there are definite counterexamples, and so we have clear evidence for scattering in these systems. This is only a taste of what will be possible with the epoch astrometry from Gaia DR4 and later DR5. And lastly, if you're curious what astrometry can do for your test system, please feel free to ask me. And that's all. Thank you very much.
Thank you very much. One quick question. I think we have time for one question now. There is a question over there.
Eric Idos, University of Hawaii. Just a comment from the disk world, the protoplanetary disk world. We're starting to appreciate a nuance where we are seeing many warps and disks. And so the idea that all these planetary systems would be initially coplanar may have to be updated.
Yeah, definitely. I was certainly papering over some of the complexities there.
Okay, maybe we have time now for a very short question, if someone has. No? Okay, then thank you very much. So the next speaker of the session is Xianyu Wang, and he will also talk about misalignment.
So where are the slides? Wait a minute. Oh yeah, thank you. Hello everyone, I'm Xianyu Wang, a postdoc at Indiana University. Today, I would like to share with you our recent progress on the stellar obliquities of exoplanets. Here is a plot for the inferred true obliquity distribution for hot Jupiter systems based on the most current measurements. The x-axis represents the true stellar obliquity ranging from 0 to 118 degrees. The y-axis is probability density function. So what can you get from this plot? Probably you already know that. That is, most hot Jupiter systems are aligned. However, a significant fraction of hot Jupiter systems are misaligned. There are numerous origin mechanisms for such kind of misalignment or spin-orbit misalignment in hot Jupiter systems, which can be generally divided into two groups. Here is a summary plot I borrowed from the Albright review paper. Certainly, I won't dive into the details of these scenarios that too much, but I can tell you some basic ideas about these two groups. For the first category, the basic idea is that spin-orbit misalignment is a natural consequence of the planet or stellar formation series or processes. It is natural or universal, which can affect all types of exoplanets, not just the hot Jupiters. The second one I'll show you in the red plot. It suggests that the spin-orbit misalignment results from the high eccentricity migration or high E migration, which means high E migration is extremely violent, which can naturally lead to the spin-orbit misalignment. If this is true, this mechanism can only apply to hot Jupiter systems, not others, because especially warm Jupiter systems, they cannot form through high E migration because their periastral are too far to be tidally circularized. So if we want to distinguish whether spin-orbit misalignment is primordial or from post-formation, the one of the best way is to conduct the stellar obliquity measurements for all types of exoplanets, especially warm Jupiters. However, before TESS, only a small group of warm Jupiters got their stellar obliquity measured. Here is a plot, period mass plot for all exoplanets. Those systems with stellar obliquity measured has been color-coded, deep color, larger stellar obliquities. As you can see, most of these measurements had been conducted to those hot Jupiter systems. That's because they have the most signal, and only a few measurements for warm Jupiters. That is because detecting warm Jupiters are historically hard, at least before TESS. Okay, there are two primary reasons for this. The first one is ground-based surveys found it is very hard to detect warm Jupiters because discovering warm Jupiters requires a long time baseline than hot Jupiters. Here is a histogram of orbital period of exoplanets discovered from ground-based telescope surveys, including SuperWASP, HARTNET, HARTSOURCE, TRESS, CELT, and EXO, etc. You may find that the detection efficiency dramatically decreases beyond several days, which means those ground-based telescope surveys have hardly detected any warm Jupiters before. Certainly, we have great Kepler mission, which can build a long enough time baseline to detect warm Jupiters. However, due to a series of reasons, like limited field of view, low occurrence rate of warm Jupiters, and relatively faint hot stars, only a few detections around bright stars detected for the suitable follow-up analysis. But right now, TESS have changed this situation with its all-sky observing strategy. This is an updated histogram. TESS has significantly enlarged the whole warm Jupiter sample, especially those around bright stars, facilitating a series of studies about warm Jupiters. Okay, probably we can put this in another way, another more straightforward way. Here is the annual discovery rate for warm Jupiters. You can see before TESS, previously, the average discovery rate for warm Jupiters was below than 10 warm Jupiters per year. But since TESS data release, the discovery rate for warm Jupiters just skyrocketed, dramatically increased the number of known warm Jupiter systems, especially those around bright stars. So taking the advantage of this warm Jupiter opportunity provided by TESS, our group initiated the SOUS project to explore the stellar obliquity distribution for warm Jupiter systems. In this project has been empowered a series of excellent instruments, primarily NEWIT, HERES, PFS, and several graduate and undergraduate students just published their first paper with us. Here, in the last several years, we conducted numerous Rossiter-McLaughlin effect measurements for warm Jupiters. Here, I would like to highlight the recent work I'm leading, which contains 6 new measurements for warm Jupiter systems. Probably already know, you can see all of them are aligned. This leads us to the first takeaway from my talk. Single star warm Jupiters tend to be aligned. Maybe you're wondering the significance level of this alignment tendency. Here is a plot, probably can tell you how statistical significant it is. You can see here, the x-axis is normalized semi-major axis, y-axis is projected spin orbit angle. Here, I would like to highlight the RM measurements we contribute. Right now, it has contributed to nearly half of the whole warm Jupiter with stellar obliquity sample. Probably you don't need to do any fancy statistical analysis. You can simply get the conclusion from the current plot. It is very significant. Still, we did a significance level calculation since we are nerdy enough. It results in a 4.3 sigma level. This huge difference between stellar obliquity for warm Jupiter and hot Jupiters lead to the second takeaway from my talk. That is temperature lambda relation for warm Jupiter systems. That is, single star warm Jupiter systems tend to be aligned even around hot stars. Here, famously, the most notable feature of the stellar obliquity for hot Jupiter systems. That is, hot stars with hot Jupiters have high obliquity. So lower panel is showing the obliquity of projected stellar obliquity versus stellar effective temperature for warm Jupiter systems. You can see we have enough warm Jupiter beyond crowd break to support that. The stellar obliquity distribution for warm Jupiter and the hot Jupiters, they don't share the same temperature lambda relation. Okay, the significance level is 3.3 sigma, which means there do not spin orbit misalignment in warm Jupiter systems. Okay, let's back to our question. Is spin orbit misalignment primordial or from post-formation? Over past 3 years or more 4 years, we have accumulated many RM measurements and get such kind of observational evidence. That is, warm Jupiter tend to be aligned. This kind of alignment or tendency in warm Jupiter systems can tell us the spin orbit misalignment is not primordial. It's from post-formation. That's the last takeaway from my talk. But through this project, we also observed a series of RM measurements for compact multi-planet systems and confirmed the previous suggested by Albright 2013. Compact multi-planet systems also tend to be aligned. So this is all contents I want to convey, and I would like to share and summarize the talk here. Single star warm Jupiter systems tend to be aligned even around hot stars, and spin orbit misalignment is not primordial. It's from the post-formation. Thank you very much. Would like to take any questions.
Thank you very much. So it means that now we have time for questions, at least 2.
Yes, yeah.
Hey, Stern Carmichael, University of Hawaii. Yeah, great talk. Just a quick question. So what are the ranges of eccentricities for the warm Jupiters? And are they usually circular? Or are they still eccentric? And
doesn't matter.
This picture of alignment.
Circular or eccentric warm Jupiter all tend to be aligned. That's a fabulous question. I would like to explain more because I prepared a slide for this. Wait a minute. Oh, that's about the sample selection. That's about the significance level. Wait a minute. That's it. You want to know? So this is a plot from Huan's paper. That's about the eccentric warm Jupiter also tend to be aligned. It doesn't matter about the eccentricity, I mean, large or small. Would you want to know more? Yes. That's because a related question, why we don't see any misaligned warm Jupiter around hot stars? You may be wondering? That's because the time scale issue. Here is the title. If there is warm Jupiter there, exciting eccentricity is easier than exciting high obliquity. So if the warm Jupiter firstly get a very high eccentricity, it will trigger high migration, become a hot Jupiter. That's probably the one of the channel to become a misaligned hot Jupiter in the current plot here. Is that clear? Thank you.
So one more short question.
Hi, over here. Hi, Xianyu. Hi. Don Moto from the University of New Mexico. I probably just missed this, but are these single planet systems or are these multi-planet systems that you're studying? And that's for both the hot Jupiters and the warm Jupiter systems.
Currently, we didn't distinguish because we cannot know whether they are distant or cold Jupiters. So we just get them all.
Okay, so you didn't like perform any follow-up searches to determine whether there were other planets that could be detectable? That's true?
Mm-hmm.
Okay, great. Just wanted to clarify. Thank you.
You're welcome.
Thank you very much. Thanks again for the talk. So the next talk is by Steven. How do you pronounce your name?
Giacalone.
Giacalone. Okay.
Cool. All right. Thanks, everyone. So today we're continuing on the stellar obliquity train and telling you about some work I'm doing to study the stellar obliquity of transiting brown dwarf systems, as opposed to the hot Jupiters that people have been talking about previously. So before I start, I'm going to beat this into all your heads. What is stellar obliquity? So stellar obliquity is defined as the angle between the planetary orbital axis and the stellar spin axis. So it's exactly this angle, lambda, that I'm showing here. So throughout this talk, when I refer to systems that have aligned or prograde orbits, I'm referring to a low lambda, so lambda near 0, so transits like that. Systems that have misaligned or polar orbits, I'm usually speaking about things that have lambda near about 90 degrees, so they transit like this. And then retrograde orbits, I'm referring to systems that have lambda of about 180 degrees, so they actually orbit the stars in the opposite direction of the stellar spin. Okay, so now we can start getting into science. So this plot probably looks familiar by now. So this, again, is a scatter plot of the stellar obliquity versus stellar effective temperature, specifically for hot Jupiters. And again, like the others, I've sort of divided this by stellar effective temperature here, where stars that are cooler tend to have systems that have aligned and prograde orbits, whereas stars that are hotter tend to have systems that are very frequently misaligned, polar, retrograde. And we think that the essential cause of this has to do with the stellar structure. So the cooler stars have convective envelopes that are able to tidally realign really easily with their planets, whereas the hotter stars have radiative envelopes that can't realign as efficiently. And this carries really important implications for what we can learn about the origins of these systems. So because the hot stars don't realign tidally with the orbits of their closest companions, they essentially retain their primordial obliquities. They contain fingerprints of how these planets got there. So if we assume that hot Jupiters formed far away and came close in, we can learn about the mechanisms that brought them into these close-in orbits by studying these obliquities. And this has been done by many folks, including like Milena Rice, who is here. And they've essentially argued that because of this distribution, it favors high eccentricity migration as the origin mechanism for hot Jupiters versus something like disk migration or in situ formation. And so the question that I've become enamored with over the last couple of months is, can we repeat this exercise for close-in brown dwarfs? So again, this plot that I was showing is just hot Jupiters, things with masses up to about 13 Jupiter masses. But as soon as you enter the brown dwarf regime, so about 13 to 80 Jupiter masses, do we see the same trends, or does it diverge? And the reason why this is so interesting is because brown dwarfs, especially in close-in orbits, are really cryptic objects right now. So Noah Val gave a really good talk about this on Monday, showing that the orbital characteristics of these close-in brown dwarfs, based on that, it's really not clear how they form and how they evolve. Okay, so before I go further, I'd be remiss to not mention the study by Brendan Bowler et al. In 2023, where they essentially did this exact study that I want to do, but for the wide separation, directly imaged brown dwarfs and planets. So in their study, they found that the brown dwarf mass objects tend to have high obliquity orbits, so orbits that are misaligned with the stellar spin axes, whereas the planetary mass objects are usually consistent with spin orbit alignment. And so they use this as evidence to argue that wide separation brown dwarfs often don't form in the midplanes of their disks, and so they most likely form like stars very often. So not like through something like core accretion, but instead through something like the collapse of molecular cores. Okay, so going back to the close-in objects, what I'm especially interested in is studying the stellar obliquities for transiting brown dwarf systems around these very hot stars. So the systems that we don't expect to tidally realign, and then compare that distribution and obliquity to the same distribution for hot Jupiters, and to determine if the two objects share similar origins, essentially, if the mechanisms that bring these objects close in are the same or if they're different. So in the next slide, I'm going to show you what we know so far about stellar obliquities for these transiting brown dwarf systems. Okay, So the yellow squares are the brown dwarfs, and again, all the dots are the hot Jupiters. And so immediately you see that there really aren't a lot so far. We haven't really filled out this region of parameter space, and so we don't know a lot. Like it seems, based on our first glance, that the obliquities tend to be pretty low, but we're really working with small number statistics. And so we really want to work to expand this number, and so we can learn some statistics about these systems. All right, so you might be asking, why isn't the stellar obliquity distribution more well characterized for transiting brown dwarfs? And there are two main reasons for that. The first is that close-in brown dwarfs are really quite rare. And this is something that we've known about for a while from early radio velocity surveys of sun-like stars. Close-in brown dwarfs seem to be at a dearth relative to giant planets and stellar mass companions. The second is that most pre-TESS transiting brown dwarf systems really orbited quite faint stars. So to do these obliquity measurements, you need to be doing ground-based observations that get really high signal-to-noise spectra at a really high cadence. And so that's hard to do when you have a faint star. But luckily, thanks to TESS and the many people here that work on TESS, this landscape has really changed over the last couple of years. So now I'm going to show you a quick animation that demonstrates just how much this population of transiting brown dwarfs has exploded thanks to TESS. So here you have a mass versus orbital period for transiting brown dwarfs. If the point is larger, it means it's a brighter star. And then the color indicates the spectral type of the host. So I'll click go, and it starts filling out, and we get a few discoveries in the Kepler era, but then as soon as we pass 2018, we really get a boom in the number of transiting brown dwarfs. And you'll see that a lot of these systems are very bright, and so they're very amenable to these ground-based observations that can measure stellar obliquity. Okay, so I got together with some people that care about brown dwarfs, and we decided to put together a survey, right? We have all these bright systems that we can study the stellar obliquities for, and so we might as well start going after them in a ground-based survey. So specifically, I got together with Theron Carmichael and Noah Vowell, and we decided to define a survey called the Oatmeal Survey. Oatmeal stands for Orbital Architectures of Transiting Massive Exoplanets and Low-Mass Stars. It's a little bit contrived or complicated. We couldn't find a way to fit brown dwarf into an acronym, so massive exoplanet and low-mass star sort of is a catch-all for everything in between. Okay, so again, my specific science case in this survey is I want to know what the obliquity distribution is for hot stars with transiting brown dwarfs. And I would argue that by studying this distribution, we'll be able to disentangle the dynamical evolutions of these close-in brown dwarfs. So if we assume that the brown dwarfs form very far from their stars and then migrate inward, these should result, the different mechanisms should result in distinct lambda distributions. So the first case on the left here, we have some kind of disk-driven migration. So the brown dwarf forms in a disk, migrates inward, disk goes away, you end up with mostly aligned systems. The second scenario is some kind of secular interaction with an outer companion, such as Kozai leadoff, followed by high eccentricity migration. So that would look something like this. And there are lots of studies about these, and they usually end up with different lambda distributions, but for the most part, they tend to favor polar orbits relative to other mechanisms, at least. And then the last scenario for brown dwarfs is that the brown dwarfs start off free-floating or very weakly bound to another star, and then they get gravitationally captured by our host stars, end up on very eccentric orbits, and then again, those orbits shrink and circularize, and you end up with a close-in brown dwarf. So in this case, you would essentially get a random distribution of lambda because the velocity distribution of the stars in whatever field shouldn't be very well correlated. Or, fourth option, we don't get any information about these. And it turns out that tides do actually matter around the hot stars. So most tidal realignment theories predict that there's some dependence on mass. Maybe when we get to the brown dwarf mass objects, tides really kick in and you get to realign more easily around these hot stars. So in that case, we should find some lambda that's dependent on mass and orbital period. And I think that would be really interesting as well, because we can finally start to understand how these hot stars dissipate tides in their envelopes. Okay, so how are we getting these measurements? So for the hot stars that I'm interested in, you can't really get precise radial velocities because they have very rapid rotation rates. And so you can't do the classical Rossiter-McLaughlin method that you've seen a few examples of in the previous talks. Instead, you have to do something called the Doppler shadow method. So in this method, you study the Doppler broadened line profile of your star as a function of time as the brown dwarf is transiting it. And then you see in this animation made by Marshall Johnson, you get these little variations that move as a function of time across your line profile. And by studying the movement of this variation as a function of time, you can essentially extract your lambda And one thing I'll mention is that this measurement can be pretty difficult to do for a lot of instruments. You really need a very stable radial velocity spectrograph to do this. So it's very nice that all these new spectrographs like KPF, NUID, Express, MaroonX, et cetera, have come online, because these are really the only instruments that have the precision capable of making these measurements for a lot of the systems that we're looking at. Okay, so now let's move on to some results. So this is the first result of the oatmeal survey. This is a measurement we did with KPF of the GPX1 brown dwarf. So GPX stands for Galactic Plane Exoplanet Survey. This is actually a survey that was run by a lot of folks that are here today. So thank you for finding this object that we could follow up. Okay, so on the left, I'm showing the actual KPF data, and I've drawn a black box around where we expect the signal to be. And so you can see that there's this diagonal blue line going from the bottom left to the top right. That's the brown dwarf. We expected to see it. And on the right, we have our best fit model. And so the direction of this line as a function of time essentially tells us that the orbit of the brown dwarf is aligned with the stellar spin axis. The measurement that we get is about 7 degrees. We're still working on the fit, so the uncertainties on that will change a little bit. The next thing we did is explore tidal realignment mechanisms. We wanted to really make sure that tides were too inefficient to realign this system. And so by doing this, we really we looked at a few things. We looked at specifically the resonance locking mechanism, which is one popular method of tidal realignment for hot stars. But compared to the age of this system, it's only 200 million years old, we found that it's very unlikely to have realigned the system. So the takeaway from that is that we really think that the system is primordially aligned. We don't think that tides realigned it, which is maybe telling us something about the broader population. So going back to our sample of obliquity measurements for brown dwarfs, we've added one data point, which I've circled in yellow here. Still small number of statistics, but if you suspend reality for a minute, maybe you can convince yourself that a trend is emerging. So that trend might be that close-in brown dwarfs might have a tendency for primordial spin orbit alignment, which is the exact opposite of what we're seeing for these close-in hot Jupiters around hot stars, which tend to be very misaligned orbits. And so through our survey, we're aiming to expand this by a factor of 2 to 3, at which point we should be able to say something statistically significant about the original population. Okay, put up my summary slides. So the stellar obliquity distribution for close-in brown dwarfs is currently not well characterized, but TESS has really allowed us to change that. It's doubled, probably even tripled the number of transiting brown dwarfs with that you can get lambda measurements for. Dave Latham gave a good talk yesterday where there are a few dozen more brown dwarfs in the pipeline that are going to be published. So that'll be great for the survey. Through our survey, we're going to expand the number of lambda measurements for these systems. We are very open to collaborating with other people if others are interested in taking these measurements. There are way too many systems that we can do alone, so we can take a divide and conquer approach. And there are very early hints that primordial spin orbit alignment might be common for these brown dwarfs, which is maybe hinting towards some kind of disk migration rather than scattering, which happens for the hot Jupiters. And with that, I can take questions. I also forgot to mention, the paper is also on archive as of this morning, so that's the QR code for the archive post, if you want to check it out, for the GPX1 measurement.
Thank you very much. So I think we have time for 2 short questions. We have one from Aviv.
Aviv from the Weizmann Institute. A question about your acronym, if maybe. Sure. Do you think that brown dwarfs are actually a different population from either low mass stars or giant population?
Sorry, you're asking what do I think, or just?
Do you think are they a different population, or are they actually part of the population of low mass stars, or part of the population of massive planets?
So I think that's what we want to find out, is what the answer I'll give. So yeah, there are some folks that think that brown dwarfs, especially these close-in brown dwarfs, can form in the disk like planets do, whereas the brown dwarfs in wide separation seem to form like stars a lot, and so. Yeah, maybe there's some dependence on formation mechanism with where we're finding them in the system, or maybe there's some third mechanism that tends to form brown dwarfs, but isn't as common for the stars or for the planets. Yeah, but good question. That's part of what we want to disentangle by doing these measurements for sure.
Okay, one more question, please. Second row.
Hi, Sam Grunblatt, Johns Hopkins University. You mentioned that you're using the, basically you're looking at the line profiles here to measure that. What sort of rotational speeds do you need in order to be able to do this measurement? And are there some targets where the stars are not rotating so fast so you could actually do like traditional Rossler-McLaughlin?
Yeah, good question. So I would say the lower limit for a Doppler shadow observation is probably like 20 kilometers per second V sin I. Ideally higher. It sort of gets easier as you go higher. There aren't any targets that I'm looking into that orbit these hot stars that have lower V sin Is. They all tend to be pretty fast rotating. But there are plenty of brown dwarfs that orbit cooler stars that are like tidally detached that you can do the classical Rossler-McLaughlin for.
Okay, thank you very much. Again. So the last talk of this session is from Mutian Wang from Nanjing University about multiple planetary systems and things like that.
Thank you. Hello, everyone. I am Mutian from Nanjing University. I'm a graduate student. And today I'm going to talk about circumbinary planets. And as has shown by this cartoon, circumbinary planet is a type of planet in a binary system, but they are not orbiting either of the stars, but both of them. So although there are over 5,000 of exoplanets discovered to date, the circumbinary planets are still very rare. Most of them are discovered by the transit method from the Kepler or TESS mission. And you can see from this mass and radius diagram that the most abundant type of planets are the Jovian planets and some smaller planets. And in the intermediate region, the sub-Saturn mass planets, they are less populated. And what's interesting is that most of the current circumbinary planets lies in this regime. So maybe we are probing a very volatile rich population. However, there is some counter argument toward this. So for transiting circumbinary planets, a very complicated thing is the stars are going around. You can see from this picture that the stars are catching and falling behind the planets, almost producing a very complex and irregular transit patterns for this planet. So there are very large variations in the transit patterns for this planet. And you can see this is the transit timing variations of the circumbinary planets. And watch out the Y scale of the axis. We are talking about variations up to 2 days. But actually that has some very rich information for the overall system. The amplitude of the TTVs can give you an idea of the total mass of the binary. And also the planet can transit the star at any different binary phases. So that can sample different binary motion, and that can give you an idea of the total mass of the binary too. So if you simply phase fold all the light curves of the circumbinary planets, this is the scrambled light curves you will get. The transits are everywhere. They simply did not add up together. So you cannot achieve better detectability toward the smaller stars. So this is the argument to why we are only observing the very large circumbinary planets for now. And another missing piece of this current circumbinary planet is that because they are discovered by the transit method, so they are extremely coplanar to the binary plane. But it has been long conjectured that there must exist a population of misaligned circumbinary planets because we do observe some misaligned circumbinary disk. And the theorists have worked on this for a while, and they found the planets down to terrestrial planets can go on and form in such very extremely polar protoplanetary disk. And there is also a recent claim about the first evidence of the polar circumbinary planets around a polar disk. You can see the dust disk is very far away from the truncated disk, the truncated edge. And there's a gap between the disk, the gas disk and the dust disk. So it has been postulated there is a planet there, but we also know the gaps in the protoplanetary disk not always associated with the planet. So it's not a firm evidence, and the misaligned circumbinary planets are way to be discovered. So back to the system of the topic today, TOI 1338. Before TESS, it's only known as an eclipsing binary. And after TESS is launched, it discovered a planet on the 3-month orbit. And later, a standalone RV campaign revealed there is a outer non-transiting planet. So this is the second multi-planet system in the circumbinary system and the first circumbinary planet system for TESS. However, for now, there's still some missing information in the system. For the RV method, we don't know the inclination of the planets. So we don't know if this RV planet is misaligned or not. And the RV standalone analysis did not reveal any mass constraint on this transiting planets. That's why we decided to revisit this circumbinary planet system. So as I have told you, this system is very complicated dynamically. So we need to really carefully deal with the binary motions, perturbations, something like that. So we performed a photodynamical analysis to this system and compare with all the observational data available. So that include all the transits of the inner planets and plus the 3 transits observed in the primary mission. There are 7 more transits collected. And also the eclipse profile gives an idea of how the binary moves around. And most importantly, the very precise RV will give a full orbit solution of the binary and also the outer planet. So after we precisely solve the binary motion, we found there's an additional TTV term that cannot be counted by the binary, and that is associated with the outer RV planet. Actually, different orbital configuration of the outer RV planet will induce a different pattern of the TTVs of the inner transiting planets. And we can leverage this to give a constraint on the orbital architecture of the RV planet. So in this plot, I'm showing the overall dynamical feed, the quality of the overall dynamical feed under different assumption of the outer planet's mutual inclination. We do observe there's a gradual decrease of the chi-square toward the lower mutual inclination of the RV planets. And in this way, we can constrain the RV planet is indeed coplanar with the binary plane at a level of 10 degrees and 20 degrees for the upper limit. And plus the RM observation due to the primary spin axis and the inner transiting planet's orbit, they are also aligned. So now we have a transiting planet, it's aligned with the binary plane, and the outer planet is also aligned with the binary plane. So everything in this system is aligned, including the spin axis and all the orbits. So this is consistent with the general trend that these close binaries will have a more aligned protoplanetary disk, while for the y-orbit binary, they will have more eccentric and more misaligned disk. As for the transiting planet, this is a sub-Saturn size of planet, but we constrain the mass to be like an Earth, super Earth size planet. So this gives a very overall bulk density around 0.13. So 3038b is among the puffiest planets in the circumbinary planet population, even around the planets around single stars. In this MR diagram, I'm showing a set of low density planets that has insolation information marked. And you can see there are some planets that are irradiated to be this puffy, but not the case for the 3038b because it's very cold. And so there is no other source of heat. The eccentricity is very small. It's very far away from the stars, so tides might not be at play. And this will give sets the 3038b will have a very massive envelope, perhaps larger than 50%. There are also other causes like it could have rings or high altitude hazes to give this anomalously high radius. But nevertheless, we can conjecture if this is the real density for this planet. For the superpuffs, they are believed to not form in the location they currently in, because in the in situ formation for these superpuffs is very slow. The gas accretion rate is very slow. They might have migrated from the colder part of the protoplanetary disk, where the disk is cooler and the gas accretion could be more efficient, and they can acquire such massive envelope. So the migration scheme for superpuffs is also aligned with the formation scenario for the circumbinary planets, because for in the inner region where most of the circumbinary planets are found, the binary will exert very strong torques to the gas and the dust, and making the local growth rate of these planets very inefficient. It would take around 10 million years time for a planet to grow this large. So circumbinary planets might have formed from the outside and they migrate in. So that's all of my talk. We found in this circumbinary planet, we found the RV planet is still coplanar to the inner binary plane. It's a fully coplanar system. And we revealed that the inner transiting planet is indeed a puffy sub-Saturn and has a very massive gas envelope. And this suggests that the whole system formed in the single flat disk. There's no disk breaking or warping. And both of the planets might migrate from the outer part of the disk to this current location. And thank you.
Thank you. So before the poster session, I think we have time for 2 questions, something like that. It's over there.
Great talk, thank you. You at one point showed the phase folded RVs for planet B.
Yeah.
But Matt and that group did not report any detection for planet B. So I'm wondering.
Oh, you're asking why the previous study did not detect planet B, but
well, in your phase folded RVs, it seemed like you showed somewhat of a sinusoidal signal, but yeah, it was my impression that had not been shown yet from that same RV data set.
It is the same RV data set.
Right. So then, yeah, do you mind going back to those RVs?
This one?
Yeah, down in the bottom right there, TY 1338b, those are the RVs phase folded onto the period of the planet, right?
Right.
So are you claiming that this is a significant sinusoidal signal in this data set?
I don't know the significance, but actually I did not use the same data set because in the Discover paper, they used both HARPS and espresso data. But actually I found there is a systematic difference between 2 data sets, because when you subtract the common binary motion, there is still a very strong residue in the HARPS RV. that at the binary period, and this amplitude is very large. Perhaps it's obscuring the RV signal of the inner planets in their work.
Gotcha. Okay.
So I decided not to use the HARPS RV at all. There may be some issues in the data reduction, but I don't know the exact reason for that.
Gotcha. Cool. I would love to follow up with you on this. This is really interesting.
Thanks.
Okay, and one question over there.
Thank you. David Martin, Tufts University, just at the back here, directly in front of you. For starters, welcome to the field of circumbinary planets. It's wonderful to have graduate students working on this. This is magnificent work. Can I briefly respond to Dom's thing? Basically, he did a better job than we did. We, in the paper, this is not downgrading at all the work, the wonderful work that Matt did, but our purpose was purely to show we could find circumbinary planets in RVs only. So our fit was purely RVs, not a photodynamical fit like this. So he has the extra information from simultaneously fitting the photometry in the RVs. That's how he could eke out, I believe that's how you could eke out a signal for planet B, whereas for us, RVs only, B does not show up. So, you know, you did a terrific job to find that. I'm really just curious what you're gonna do next with this. You built this beautiful tool. You know, what are you gonna apply this to next? Like the other circumbinary planets, find some new guys? Like, what are you thinking?
Actually, that's the question. I'm not aware of any other systems that needs to do the photodynamical analysis.
Well, we could do like TESS plus Kepler, for example. So I don't know, there was some cool options, but you got a great tool, so it'd be cool to do some stuff with.
Yes, that's definitely can be done to any circumbinary planets, I think.
Yeah.
Thank you.
Okay, so thanks again, and thanks for all of the speakers for this first afternoon session.
All right. Welcome back, everyone. Let us begin the final session today, Stellar Astrophysics. We will begin this session with a talk from Zitao Lin, who will tell us about transiting brown dwarfs.
Okay. Hello, everyone. I'm Zitao Lin, and I'm a second-year graduate student from Tsinghua University. And today, I'm going to introduce our recent discovery of some transiting brown dwarfs and some interesting phenomena we found in these systems. Okay, let's start. Next page. Oh, that's fine. Oh, sorry. Okay. Yeah, I think it's fine now. Okay, so as many of you know, brown dwarfs are the important transition objects to bridging our knowledge about stars and planets, but our understanding of them still remain limited. For example, brown dwarf desert is an interesting but unresolved phenomenon. We found it is driest for closing brown dwarfs, but we still want to understand more about its origin. So to further understand brown dwarfs, transiting brown dwarfs is an ideal sample. We can combine the radial velocity data and transit data to constrain their mass, radius, and orbits very well. In the meantime, we can infer their metallicity and age from the characterization of the host stars. Then, with this rich information, we can study the demographics to understand more about brown dwarf deserts, like analyzing the eccentricity distribution following this widely cited work. In addition, transiting bound-off is also ideal for improving theoretical models. Like in the right panel, models can predict the radius evolution on the different mass. And the precise parameters of transiting bound-offs can become a very powerful observational constraint. However, up to now, only about 50 transiting bound-offs has been discovered. So to support such studies, the first step is to enlarge the sample size. So we conduct some follow-up observations of these 3 candidate systems found by TESS. We use the data from these instruments to characterize the bound-offs. And here I show an example light curve and RV curve. Most of these observations are applied by Tianjun Gai as part of his work with RV in TESS SG1. Then as a result, we found 2 transiting bound-offs and 1 low-mass star. Our precision on the object's radius and mass can reach about 5%. And this is limited by the characterization of the host star. So we can see TESS provide a very good opportunity to build a high-quality bound-off sample. So these are the basic information about our observation. Then in the following part, I will introduce some interesting phenomena we found. And let's first focus on the last system, TOI 2521. So we can see with its mass and radius, it is a slightly evolved star. And we can constrain its age using isoquant, and the result is about 10 gigayear. And when we look at its TESS light curve, we can see this obvious with rotation signal, and the period is about 7 days. However, it is very strange because as you may know, old stars do not rotate so fast. Like in this plot for general chronology, and 10 gigayear star should locate like this, rotate much slower than tens of days. But our measurement is like here. So how to explain this? We think a suitable scenario is a spin orbit synchronization. We can see the rotation period is close to the companion orbital period. And we can also calculate the synchronization timescale, and the result is about 100 million years, much smaller than the system age. This also supports the synchronization scenario. So we think this abnormally fast rotation of the host star is a potential evidence for the tidal spin orbit synchronization. And we also found a similar case for another target, TOI 1608. And these 2 systems can be interesting targets to study and constrain tidal theories. Then let's jump to the next topic. As I mentioned in the introduction, we can compare the bound-offs with the theoretical models. And here, and we can do this here in this mass radius diagram. And these 3 red dots are our targets, and these lines are the models for different age. Then with the estimated system age, we can find the model prediction is like this. And we can see it is bad because all of our targets are larger than the model prediction. So why is this? We found a possible explanation from the studies of giant planets. So in some works has pointed out that the radius of planets can be inflated by the radiation from the host star. Like we can see the positive correlation between the incident flux and the radius of planets. So can this mechanism explain the inflation of our targets? Or more generally, can bound-offs and low-mass stars also be inflated by radiation? So to figure out this, we collect a sample of discovered transiting bound-offs and low-mass stars, and we fit a similar power law equation for this sample, and the result is shown here. And let's look into these results. First, we can see the dependence on the incident flux is positive and statistically significant. So this may indicate the brown dwarfs and the low mass stars can also be inflated by the radiation from their host stars. And we can also compare the results with the giant planets, and we can see the dependence of the brown dwarfs and the low mass stars are much weaker. So this is what we should expect, because the gravity on the brown dwarfs and the low mass stars are larger, so they should be more difficult to inflate. However, when interpreting these results, we should also notice some caveats. First, the parameter incident flux here may not reflect the true underlying physics. For example, the incident flux is also related to the separation between the companion and the stars. So the positive relation we found here may actually rely on the separation, and this can be the prediction of other theories like tidal inflation. And another caveat is that we do not consider other important factors like age. So age can influence the radius very much, like we see in the theoretical models. So this can also influence our conclusion. And I know Seven also makes some efforts on this, and you can see his poster for more discussion. Then in the final topic, we can check the eccentricity distribution of the brown dwarfs. And we can see in this mass eccentricity diagram, the transiting sample seems that the transiting sample can also be divided by this brown dwarf desert like RV sample. However, you may also remember in Noah's talk on Monday, he showed an updated sample where this division is not so pronounced, especially in the mass visual space. And here, I also want to emphasize that there's another trend for the eccentricity. Like in this period space, we can see the short period brown dwarfs tend to have low and zero eccentricity. And this is consistent with the tidal circularization. So I think we still need more data to consider these complex factors and finally find the imprints of the from the brown dwarf desert. And here I also want to highlight an ongoing work. This is an outlier in this plot. And this is about 800 million year system. And with a radial velocity measurement, we found its eccentricity is large. But in the Rosita-McLaughlin observations, we found it has a low obliquity. This means this companion is in an eccentric but aligned orbit. So this is very interesting, and this system is still being analyzed by Qinru Hu, also a student from Tsinghua University, and the paper is coming soon. At last, TESS provide us an unprecedented sample of transiting brown dwarfs, which are important and ideal for studying demographics, tidal interactions, radial inflations, and many other things for brown dwarfs. I list the interesting phenomena we found here, and I'll end up here. Thank you, and I'm happy to take any questions.
All right, any questions for Zitao? Around the back.
Hi, really nice work. For TOI 1830, at least as a comment, I don't really think it's an outlier because we expect the circularization timescale to take a lot longer than the realignment time scale. So it could have been realigned, but just didn't have enough time to circularize. But as a question, do you have the rotation rate of the star? Do you know anything about like synchronization, for example?
Yeah, so I don't remember the information about the rotation of the whole stars. Sorry, yeah, but I also agree that what you mentioned is actually the potential explanation for these systems. Thank you.
Awesome, thank you.
We have time for one more quick question.
Hi, Linhao Ma from Princeton here. So if the inflation is caused by tidal heating the planets, I think that should only apply to very eccentric orbits. So do you have any comments on any possible correlations between the eccentricity and the inflation of the brown dwarf?
Yeah, so you mean the tidal inflation should correlate with the eccentricity?
Yes, because more eccentricity, if you have zero eccentricity, you don't have any tidal heating in the brown dwarf.
Yeah, I also think so, but yeah, we do not do such work to consider the correlation between the inflation and the eccentricity. Yeah, I think it's a very good idea to check the differences between the inflation from the tidal and the inflation from the incident flux.
Okay, thank you.
Okay, please post further questions on Slack. Let's thank our speaker again. Now, binaries part 2. Our next speaker, Dominick Rowan, will talk to us about measuring fundamental stellar parameters with eclipsing binaries.
Hi, everyone. My name is Dom Rowan. I'm a grad student at Ohio State. I'll be applying for postdocs this fall. And today I'll talk about how we've combined Assassin and TESS to characterize eclipsing binaries. So far this week, we've heard that eclipsing binaries are just false positives in our exoplanet searches. Maybe that's true for some of you. It's okay, my feelings aren't hurt. Yeah. I hope I can convince you that they can be so much more. Eclipsing binaries are also the most effective way to measure precise and accurate stellar parameters. The idea is simple. You take a detached eclipsing binary, where we assume that both stars have evolved effectively independently. We get photometry, we measure the light curves, we see periodic dips as the stars pass in front of each other. We get spectra, measure radial velocities for both components. And by combining just these two data sets, we can get a complete picture of the system. We can measure both masses and radii totally independent of stellar models. And this means detached eclipsing binaries are a great tool to calibrate and improve stellar models. This is not a new idea. It's been done for many years now. This figure shows probably the premier sample of detached eclipsing binaries from Torres et al. It's about 100 systems on this figure where we measure masses and radii with fractional uncertainties less than around 3%. And these results have been widely used to calibrate other mass estimation methods, to make direct comparisons to stellar models, and to characterize exoplanets, right? We need to understand the host star if we're going to characterize planets. And since then, we've continued to observe more detached eclipsing binaries, made more of these mass and radius measurements, but we're still sitting at around a few hundred systems with these precise mass and radius determinations. So clearly, there's an opportunity to expand the sample considerably with large all-sky surveys. Pretty much every photometric survey has observed large samples of eclipsing binaries, usually as part of some variable star search, classifying systems with machine learning. Today, I want to talk about how we can combine two of these systems, TESS and Assassin, to study binary systems in new ways. We've heard a bit about Assassin throughout the week. Assassin is the all-sky automated survey for supernovae. The basic stats for Assassin are on the screen, but the main idea is that with Assassin, we observe the entire sky in optical light with daily cadence. And so this makes Assassin a great tool to study the variable universe. Indeed, there's been more than 400,000 variable stars identified in Assassin, including tens of thousands of eclipsing binaries. A few years ago, we released the Assassin Eclipsing Binaries database that includes more than 35,000 detached systems. We fit all of their light curves using Phoebe, which is one of these light curve modeling tools for EBs. This figure is showing some of our Assassin light curve results. Those Phoebe models are overplotted in black. And we're measuring parameters related to the orbits of the stars, like the eccentricity, the inclination, as well as stellar parameters like the ratio of the effective temperatures and the fractional radii. We also put a big effort into making all this public. So we have this nice interactive online database. So you can download our full catalog. You can enter a search, say you're interested in main sequence binaries that are eccentric, enter that query, download the subset of your results. You can also click on individual systems, check out their light curves, their Phoebe fits, you can download the data directly from our site. So hopefully this is useful for you if you're interested in binary systems. But today I want to talk about how we've added value to this Assassin catalog with TESS. TESS complements Assassin in a great way, right? You can take this large all-sky survey in Assassin and then get higher precision, higher cadence photometry over smaller patches of the sky. And I'll start with our extra physics binaries. When we were working on this Assassin catalog, we visually inspected tens of thousands of TESS light curves as a way to confirm orbital periods. This is an example of why we might want to do this. In this Assassin light curve, the primary eclipse is pretty deep. It's around 0.75 in phase here. And you can imagine if you were doing this fit in an automated way on tens of thousands of systems, you might miss the secondary eclipse. But with the TESS light curve, it's pretty apparent that, oh yeah, we've gotten the orbital period right here. It's not off by a factor of 2. And really, this was our primary goal when we started visually inspecting these TESS light curves. But along the way, we identified hundreds of systems with additional features in their light curve, additional variability beyond just that main eclipsing signal. So we broadly call these our extra physics binaries. There's 766 in our catalog. This figure is showing 4 of the examples, the TESS light curves of these examples. The top left is an example of a quadruple system, a doubly eclipsing binary. So we see these additional dips different to that main primary and secondary eclipse. The top right is an example of a binary where one of those stars is heavily spotted. So we see this additional modulation over the course of that orbit. These spots evolve over the surfaces of these stars over the course of a TESS sector even. So that scatter and that green light curve up there is real. And the bottom 2 panels are showing different examples of eclipsing binaries and pulsating components. We divide all of these 766 systems into different categories. They're all labeled in the legend here. And this figure is showing all of our systems on the Gaia color magnitude diagram. So you can immediately see that the spotted stars, which are in green, make up the biggest group here. Most of these are on the lower main sequence or on the giant branch. There's a few subgiants in this sample as well. And a fair number of these targets are X-ray detections. The Gamma Doradus pulsators all fall in this nice little clump on the CMB where we expect them. It's a bit hard to see, but they're all in that red circle. And there's also a number of systems below the main sequence. These are eclipsing white dwarf CV systems, as well as some subdwarf binaries where we see reflection effects. There is some science to do, though, beyond just looking at the neat light curves. I'll just talk about one example here. For the doubly eclipsing binaries, those quadruple systems, we're interested in understanding the dynamical formation and evolution of the system. So one piece of information we immediately want to know is what's the second orbital period. This top panel is showing an example of one of the TESS light curves that we flagged as a possible quadruple during visual inspection. You can see there's all these additional dips that are clearly at a different period than the one we found with Assassin. So we just subtract off the signal using Phoebe, and that bottom panel is showing the phase folded results from those residuals. We look at the period ratio distribution for all of our systems. It's about 150 or so in the catalog. We find a slight overabundance of systems with a period ratio of 3:2. This is something that has been seen in some other catalogs of quadruple systems of doubly eclipsing binaries, but it's really difficult to place statistical significance to this detection because we suspect that anywhere between 1/5 and 1/4 of these could be blends from nearby eclipsing binaries along our line of sight. So if you want to check out any of these systems, once again, you should go to our website, Assassin, and go to the binaries tab. You can look at all the light curves. You can download the test data from here as well. Click on the systems from the CMD. There's lots of cool stuff in here. But I want to get back to this idea of measuring masses and radii. This is what makes eclipsing binaries so awesome. And we need to add in spectra if we're going to do this. And we should be strategic. I don't have unlimited observing time. So if we're going to collect spectra and measure radial velocities, what type of stars should we do this for? To return to this figure from Torres et al., there's clearly a lot of points around sun-like stars on the main sequence, but there's parts of this parameter space that are relatively sparse, like on the lower main sequence, or we specifically focused on the giant branch. And there's a number of physical processes in giant stars like convective overshoot and mixing and rotation that alter their observed properties, where it'd be great to have these dynamical mass measurements. And so we've been targeting 10 eclipsing red giants using a variety of spectrographs. This figure is showing how we selected those systems just based on the Gaia CMD. We tag all of our Assassin eclipsing binaries as being on the main sequence, subgiant, or giant branch. That's what all these solid and dashed colored lines are showing. And we selected these 10 systems in particular because they were bright enough to get precise radio velocities, and because they're nice detached systems, so periods ranging from 30 to 80 days or so. We've been following these systems up with APF, Pepsi, and Chiron, so we have full coverage all over the sky. I'll skip over all about how we measure radio velocities and just say that we're getting RV precisions of a few hundred meters per second here, but this is totally fine for these detached eclipsing binaries where the velocity semi-amplitudes are tens of kilometers per second. Originally, the plan was let's just fit the assassin light curves with the radio velocities with Phoebe. I mean, this is how we selected the targets in the first place. And for this example, it works great. The assassin light curve is awesome. We have these nice, well-defined eclipses. We can get the fractional radii, the inclination. When we add in the RVs, we get nice mass and radius measurements with uncertainties of a few percent. But there are some cases where we could benefit from having additional photometry, like this one here. This star is actually a bit too bright for assassin. It's near saturation, so causing all these systematic effects, lots of scatter. So we're interested in looking to see if there's any additional photometry from TESS. For 4 of our systems, that's the case. So here's the TESS light curve, where we have both eclipses that aren't cut off between sector gaps or the gaps during downlink. And we extract these light curves using the TGLC pipeline. Even if multiple sectors of data are available, we're just going to stick to one here. We don't really benefit too much from dealing with all the stitching issues, especially because we already know the orbital period from assassin. And so the idea is to fit all 3 of these data sets simultaneously. The main improvement that adding in the TESS light curves gives us is improving our radii constraints, right? Because that tells us the ingress and egress times of those eclipses. So I'll show you I'll compare the radius posteriors before and after we add in the TESS light curve. So this is just showing that same assassin plus RV fit in red. We actually don't do too bad in measuring the radii of these stars, uncertainties of 0.1, 0.2 solar radii. But when we add in the TESS light curve, we can do a lot better. So decreasing those uncertainties by around a factor of 2. This is really the main improvement that we get from adding in these TESS light curves. This is, the same thing is true for the other 3 systems where we have good TESS data. Okay, so we do this for 8 binaries in total. We've measured masses and radii with fractional uncertainties less than around 3%. So we've hit our goal here. 2 of our systems that we were following up ended up being single line spectroscopic binaries. So we've removed them from our sample. And this figure is showing our mass and radius measurements compared to that TORS et al. Catalog. So clearly we're starting to fill in this new parameter space. The majority of our systems also end up being twins. This makes them a bit easier to measure RVs for. One of those systems, though, you can see still has a companion that's hanging out on the main sequence. So this is really the first dedicated spectroscopic survey of eclipsing red giants in the Milky Way. We're continuing to observe more systems and making more direct comparisons to evolutionary tracks. So definitely stay tuned for the full catalog. I think with that, I'll stop here, but I'm happy to take any questions.
Any questions for Dominick? There's one back there.
Tara Featheroff, UC Riverside, great talk. I'm really interested in these extra physics binaries. In particular, how does your search do with eccentric binaries, which may induce extra physics?
Yeah, that's a good question. So the question was, how do eccentric binaries, do we see additional oscillations in those systems maybe? Yeah, that's a point I've been thinking about a little bit this week. I've learned more about some of those types of systems. There are some systems that we classified in those things like pulsating groups that don't really fit in nicely. The light curves don't fit in nicely with Delta Scuti stars or anything like that. So those might be some examples. So if they're in the sample, I'd expect them to be in that pulsating group. We have a number of eccentric systems. There's 1 or 2 heartbeat stars in here as well. So it'd be worth checking those out.
Hello, Dom, who's interested in EBs. I'm also Dom, who's interested in EBs. Great talk, thank you. This is wonderful work. I'm just curious to hear your thoughts about the selection of TESS sectors, because I'm wondering if you are taking into consideration precession of a potential binary, and like having that longer baseline from multiple TESS sectors might be beneficial in that case, or?
Yeah, that's a good question. I haven't thought about it too deeply, but there's definitely cases where we do have multiple TESS sectors separated by months or years, and we do start to see some of the effects of precession. We haven't done a systematic search for those kind of systems, Definitely something we can add to the to-do list, though. And the Assassin catalog would be a great place to start if you're interested in doing any of those kind of searches yourself.
Any last questions? If not, let's thank our speaker again. Binaries Part 3. Our next speaker will talk to us about X-ray binaries. And please welcome Masafumi Niwano.
Can you hear me? I'm Masafumi Niwano from a postdoc in Tokyo Tech. We studied star and disk coupling of B stars in B X-ray binaries using TESS data. This figure is a schematic image of B X-ray binaries. B X-ray binaries are a binary system composed of a B star and a compact object. A compact object is usually a neutron star. B star is an early type star having a circumstellar disk. Circumstellar disk is an optically thin disk structure formed by viscous diffusion from masses expelled from B star. And B star shows two types of X-ray outbursts, normal and giant outbursts. Normal outbursts are periodic and regular outbursts. They are initiated when the neutron star passes a periastron and capturing a mass from circumstellar disks. On the other hand, giant outbursts are irregular and bright outbursts. Physics behind these outbursts are still not well understood. So that is making it crucial, making it essential to understanding the nature of circumstellar disks. B star shows two important observational features. One is an IR excess. This refers an excess component in IR band. And this is originated from a thermal free emission from the circumstellar disks. And the next is a periodic optical flux oscillation derived from their rotation and pulsations. One critical open question about B star is what drives mass ejection? And the main candidates are their rapid rotation, non-radial pulsations, and magnetic field. But none of them can explain sufficient mass ejection. And addressing this problem is the main objective of our study. Our purpose is to constrain a relationship between B star activities and circumstellar disk evolutions. This is important to understanding mass ejection mechanisms of B stars and thus outbursts in B X-ray binaries. Therefore, we analyzed the TESS light curves and multi-wavelength light curves of 5 galactic B X-ray binaries. And we utilized TESS light curves and X-ray light curves of Swift and Maxi, and optical light curves of ZTF and Atlas, and near-infrared light curves of Gattini. The dataset covers 4.4 years from 2018. This slide shows analysis procedure of TESS light curves. In brief, we applied Omskagel techniques to TESS light curves to obtain amplitude spectra. And then we extracted peak from the amplitude spectra to obtain frequency and amplitude of each flux oscillation mode. This figure is an multi-level light curves of 4U01, 15 plus 634. And top to the bottom is an X-ray optical and near-infrared light curves. X-ray light curves show a significant outburst, and this is likely to be a giant outburst based on its luminosity and lack of orbital periodicity. And OIR light curves show long-term variations over hundreds of days. And this figure shows near-infrared light curves and OIR color variations. This figure shows redder when brighter tendency. And these OIR features suggested that the observed OIR variations are derived by the disk evolution. These giant outbursts and disk-derived OIR variations are confirmed in all of 5 sources. This is an amplitude spectra of 4U0115. All of 5 sources show the main peak in frequency range in 2 to the 4-day inverse range. And the main peaks show an amplitude variation in variation in amplitude, the amplitude. And this slide shows the peak relationship of peak amplitude and IR excess. Top panel is an amplitude spectra, and bottom panel shows an IR excess and peak amplitude. 4 out of 5 sources show at least one peaks showing amplitude and IR excess anti-correlation, including main peaks. And this anti-correlation suggested that the pulsation and disk growth, amplitude and disk growth are anti-correlated. This may disprove the conventional pulsation-driven mass ejection model. Therefore, we examined several hypotheses to explain anti-correlation. The first is assuming anti-correlated peaks are rotation-derived peaks rather than pulsation. However, a few anti-correlated peaks having rotation-derived feature, and making this hypothesis unfavored. Next hypothesis considering the flux variation. Peak amplitude variations are caused by changing amount of reprocessing of circumstellar materials. But this scenario is difficult to explain the coexistence of anti-correlated and non-correlated peaks. Therefore, we consider the most plausible explanation is there is indeed anti-correlation between pulsation and disk growth. So we have to make a physical picture of explaining the pulsation and disk growth anti-correlation. Pulsation in massive stars are driven by kappa mechanism, where kappa is an Roland opacity. Temperature range where temperature and kappa are positively correlated. Kappa variation acts as a positive feedback on thermodynamic fluctuations. And therefore, pulsation must be most active when temperature and kappa curve are steep. A slope of temperature and kappa curve are most steep. And the other temperature range might be a pulsation active state. When considering a lower temperature side, a lower temperature might be caused by expansion of the star. Then the outer layer of star is less bound, and it might be favorable for mass ejection. On the other hand, considering a higher temperature side, a higher temperature produces stronger radiation pressure, and this also is favorable for mass ejection. In any case, pulsation in active state is expected to be favorable for mass ejection. So we found an anti-correlation between flux oscillation amplitude of main peaks and IRXS by analyzing test light curves of 5 galactic PXBs. And therefore, then the conventional pulsation-driven mass ejection model may be incorrect. Thank you for listening.
Questions for Masafumi? Keaton?
Hi, I'm Keaton Bell from the City University of New York. This is very interesting. Since these stars are pulsating, can you get any information from the pulsations about the rotation rates of these stars? And if so, does the rotation rate relate to anything like the disk size through the infrared excess?
I don't get to your question.
From the pulsations, you could, in theory, measure the rotation rates from the splittings of the modes. Do you have rotation rates for these BE stars?
No, but instead of that, we estimated the mass and radius of each B star, and estimate the critical rotation velocity, and we compared the frequency of each peaks and with the estimated critical velocity.
Thanks.
We have time for one more question from the audience. If not, let's thank our speaker again. Okay, now we shift gears to stellar variability. Our next speaker, Linhao Ma, will tell us about the variability of blue supergiants.
Hello, I'm Linhao. So I just started my postdoc last week. So please don't roast me too hard. Yeah, so this is some project I did last summer with these wonderful people. Oops, where's that? Yeah, with these wonderful people at Max Planck Institute for Astrophysics. So basically, we investigated something about blue supergiants, as you can see from the group photo here. So before I get started, let me ask you a question. So how many of you have ever seen a blue supergiant with your eyes? Raise your hand. Okay, it should actually be more than this. Why? Because blue supergiants, they are actually the brightest star visible in the sky. And as an astronomer, if you don't know any other stars, you should at least recognize this, which is Orion. So this is a photo I took like 8 years ago in my hometown, which is one of the most populated, highly light polluted regions in the world, where there's almost no stars in the sky. But even in this photo, you can see Orion. And it turns out that a star called Rigel in this thing, it is a blue supergiant. So if you ever look up in the sky, you should actually already have seen it. Okay, so blue supergiants, they are so bright, and they can do a lot of things to the universe, and they're so common. But it turns out we actually do not understand how they form. So as a theorist, so usually when we want to understand the evolution of a star, we go to, we put the star on an HR diagram, as you can see from here. So basically the blue supergiant is like a distinct class here. Then we make some models and then put these stellar tracks on it. Then we realize, okay, that's cool. So these blue supergiants, they're on these stellar tracks, so they must be the stars at this evolutionary stage. But is that true? It turns out it's not. The reason is that these stellar tracks, they don't tell you how much time they spend in each region in the HR diagram. And now we put some dots on these stellar tracks, and you can see that, so these dots are put with like equal time interval. So you can see that there are so many dots here on the main sequence, but not so many there, which means that if a blue supergiant actually lives in this stage, their lifetime is really short, so we shouldn't see so many of them. But what we found from the observations is that there are so many like blue supergiants here compared to the other stars we see on the HR diagram. So the single stellar evolution theory alone cannot actually tell you how these blue supergiants form, even though they are so common. So as a theorist, we then we think about, okay, so what can we do around about the theories? So some people thinking about, okay, so maybe these blue supergiants, they're main sequence stars with small hydrogen cores. Maybe they are like helium-burning stars with large helium cores. Or some people are arguing maybe they're merger products. So that could basically just extend their lifetime on the HR diagram in that region. So I'm not going to comment on which of the theories is correct because I don't know. But the thing here you notice that they all have something to do with the core of the star. But the problem is, if you have a blue supergiant like this, you look at it, can you see its core? No, you cannot, right? Because it's not transparent. What you see is actually the photosphere of the star. But it turns out, how do we know like any information about the core? It turns out that stars, they're not just like a ball like this. Actually, they pulsate like this. So if we learn some information about pulsation and the pulsation excited by some mechanisms in the core, we could actually learn something about the core, and we may be able to distinguish which of these theories are correct to explain blue supergiants. So this is basically the ideal astroseismology. So I have a blue supergiant here, some core hidden inside, but they propagate some waves outside, and they carry some information. And it turns out that some people have been arguing that there's certain observable called the period spacing of some certain oscillation modes, where you can actually distinguish in the parameter space about these different formation channels. Okay, so this basically enables us to, motivates us to study the photometric variability of blue supergiants, aiming to find some of these positions. So astroseismology has been, it's not a very new topic. So people think about, okay, so maybe we can use things like Kepler to do our analysis of blue supergiants. So why don't we use Kepler? First, this is a TESS conference. Second, It turns out that Kepler is great in doing astroseismology, but only to a certain portion of the sky. So it turns out there are no like 0 or maybe 1, I don't know, blue supergiant in that region. So that's why TESS comes into play, because TESS has these 4 cameras spanning this 24 degrees times 960 degrees angles, and in 4 years, it's going to really do this all sky observations. So I would say this is really like a buffet of blue supergiants that all you can see here. So yeah, this is cool. So we're going to use TESS. Okay. So the rest of scientific context. So basically we select 124 OB stars with spectroscopy measurements, and we select a small portion of the actual diagram to define them as blue supergiants. I just comment that TESS is great because it's doing this all sky observations. The problem about TESS is that its pixel size is actually very large. So sometimes you find a star in some very crowded region. So there are so many other stars in the same pixel. So you don't really know which star you're actually looking at. So these are we call bad targets. On the other hand, some stars are not in so crowded region in the sky. So you can actually make sure that these stars are the things you are trying to look at. So basically after this kind of selection, we finally have 20 targets of blue supergiants, and they turn out to be all in LMC. So we're using this TESS 2-minute cadence data, so treated with a Spock pipeline, because we're aiming to look at the low frequency signal, which is mostly related to the waves that are propagating from the core of the blue supergiant. Okay, so what is the signal? So here I'm showing the light curve and the parallelogram of the signal. So you can see that the parallelogram is a shape that looks like the red line is showing here, which is fitted by this function. So in short, there seems to be a turnover at about 0.25 days, and the power goes to 0 at 0 frequency, and it has a longer tail, like higher frequency. I would say that this is very common. We see that in all these 20 targets, as you can see here, and it's quite unique and like universal. Another interesting thing we found out is that these parallelograms are based on combining like all TESS sectors and observing these stars. But if we do similar things to individual sectors, you can see that the peaks of this signal in the parallelogram doesn't look exactly the same as in the same sector. But it looks like in some sectors, the same signal like comes back after a few sectors. So I think this is suggesting that whatever is driving this signal, it must live on very short time scale, because the one TESS sector is like 27 days. So it happens on weeks to months time scales. Okay, so the basic thing here is that we see this. So can this tell us anything about the interior, the waves? So in the rest of the talk, I'm going to say some possible explanation for that. There are no theories. They have not been so carefully investigated. So basically, to understand it, we make a stellar model like this one. So they're showing a toy like 1D blue supergiant model. So the basic feature you notice that there's 3 convective zones in the model. So there's a convective zone corresponding to helium ionization, another one corresponding to iron ionization, and like another one corresponding to core convection. So the first explanation is that there could still be waves like from the center of the star that are propagating outwards, and they are excited by the core convection. The most like compelling evidence is that some people with simulation have shown that if you do such analysis, if you do calculate these waves, they provide like a shape like this, just like the signal we see, and they can be explained by the damping and excitation of gravity waves. The problem is that these simulations tell us that you're unlikely to see such a large amplitude in the signal because the waves are excited from the core and just take such a long distance for them to propagate to the surface. So it seems like this is not the most satisfactory explanation. But I would comment that the work that I mentioned, they only consider the waves that are excited by the core convection. But it turns out there are some like subsurface convection that is closer to the surface. So they may actually do the similar things and provide the signal we see. But we don't know yet because such simulations are very hard to set up. But another problem for that is that our stellar evolution model is purely computed from missing length theory. And missing length theory, everybody in the stellar astrophysics community say they're wrong. So one thing you can see is that one thing that could happen is that if you really do 3D simulations of these massive stars, these subsurface convective zones, they tend to merge together and extend all the way to the surface. In that case, what you may see is basically just the convection, the convective motions in the photosphere. And they're not related to waves because these waves cannot propagate in these regions. So if that is true, an evidence is that the turnover frequency of the signal should actually match the convective turnover frequency of one of these convective zones. And up to some factors of 2 pi, whatever, you can see that the most compelling convective zones might be the convective zones by the iron opacity peaks. But we don't know. Another problem is that simulation of this convection basically tells you that the signal should look like this. In other words, there's a plateau in the zero frequency, which is different from the signal we see. So we still don't know yet, but I hope you find this signal interesting. So I'll just leave my summary here. So the shorter summary is basically, we should look at this thing more. Thank you.
Great talk. Any questions for Linhao? Derek, in the front.
Derek Buzashi, FGCU. It was a great talk, and I totally agree with you about blue supergiants being cool and needing more investigation. I guess I'm curious about whether the low frequency power, how sure are you that it's really coming from oscillations? And I ask this just because Deneb, which of course is a much more local blue supergiant, in that case, it's not exactly in the same part of the HR diagram as your targets are, but it's not that far away. The oscillations look like they're coming from a clumpy wind because you see a polarimetric signal. So I'm just curious about whether you've considered other explanations.
Yeah, so we did consider the clumping wind scenario. So basically that idea is that what we see are just some winds launching into the out of the star. But if that is true, basically the V sin I measurements, which we have from spectroscopy for these stars, should indicate a peak frequency that is about should indicate a frequency, rotational frequency that is about the peak frequency in the signal. But we find it's not true. Actually, all these, okay, I really don't have, but actually all these peak signals are higher than what derived from V sin I. So basically, we don't think that is a very good explanation for this. Yeah.
Next question from Dennis at the back.
Dennis Stello, Sydney. So when I see a power spectrum that looks like yours, I get a bit worried because that's how it looks if I do a high-pass filter of a red noise source. So I'm wondering, have you high-pass filtered your data?
Sorry, can you repeat our question?
Have you high-pass filtered your data?
You mean there's some problem with the low frequency part?
I'm just saying, if you high-pass filter data that is basically dominated by red noise, you get a natural peak where the peak happens at a frequency of your filter.
So I'm not really the expert to answering how the bulk pipeline is actually treating all this data. But the thing I understand is that basically this pipeline is to analyze the low frequency part of the signal for some photometric like quiet stars, and then remove that signal, contributed by all other noises from the raw data of TESS, basically. So I think if those people are doing this correctly, I hope, then what we see, whether they're positions or not, there should be something from the star, not just from noise. So yeah.
Connie at the front.
Connie Arslöven. Thanks, Linhao, for a great talk. Just some information. So my student, Nadia Serebriakova, whose name you didn't mention because it's so hard, but that was at the basis of your sample, has now come to the conclusion, based on 500 stars, that above 30 solar masses is basically velocities due to turbulent pressure. Below this mass, internal gravity waves are the more appropriate conclusions. So I can share the manuscript with you. It's submitted.
Okay, I don't think we have stars above 30 solar masses in this sample. So the stellar tracks I show is there from 10 to 20. And most of these systems fall into that, but yeah, certainly we can follow up on this.
Yeah, I'll show you what we have right now. But I totally agree that we need to look better at these stars.
Yeah, thank you.
Let's thank Linhao again. All right, in this session, we have heard talks about binaries. We have heard talks about pulsations. Our final speaker for today, Shishir Dholakia, will talk to us about both of these. The floor is yours.
Right through there.
I'm entering my third and final year of my PhD at the University of Southern Queensland. Thank you all for making it all the way to the end of this day. So I mostly work on detecting and characterizing longer period transiting exoplanets, but today I'm going to be talking to you about some of the work I've been doing to detect binary stars with the technique called pulsation timing from the first 4 years of TESS mission photometry. So pulsation timing is this clever technique in which you can take the light curve of a pulsating star and you can actually get all of the orbital parameters that radial velocity gives you kind of for free. So this is really nice. Here's how it works. So you need to have a pulsating star, a coherent pulsator like a delta Scuti. And let's say it's being orbited by an unseen companion. So as this delta Scuti makes its orbit, it'll get farther from the observer. And so the light arrival time will be longer, and therefore the pulsations will arrive late. And when it gets closer to the observer, the pulsations will arrive early, and you'll detect that in the light curve. So down here, you can see you get these phase modulations that you can analyze in order to get the mass function, the orbital period, the eccentricities, etc. So this is a really cool technique that you can use. And it's been used before. So let me draw your attention to the right, the plot on the right here. And you can see all of the data points on this plot are binaries that were detected with this technique from Murphy et al. in the Kepler data set. And so this is a parameter space plot of various different ways you can detect binaries. And red over here is eclipsing binaries. In orange, we have spectroscopic SB2 binaries. And in blue, we have large baseline interferometry. And on the y-axis is the mass ratio. On the x-axis is the log of the period. And so importantly, pulsation timing is sensitive to this empty area over here. That empty area is also astrophysically valuable because in that little green area you have post-mass transfer binaries, also known as blue stragglers. One kind of that is like a type 1a supernova progenitor. And you also have some brown dwarfs and exoplanets in there. So we want to be able to search for those kinds of systems. One important thing to mention about pulsation timing is that unlike radial velocity, it's actually preferentially sensitive to longer period or more distant companions because it's looking at the actual position of the pulsating star. And so if we extend this technique to TESS, we can try to obtain orbits for binary companions to some of the brightest stars in the sky. I liked the last talk talked about Rigel, and so I can say that another famous star is Sirius, which is an A-type star with an intermediate period binary companion. So stuff like that might be accessible with TESS as well. So there's also some challenges associated with intermediate period binaries in general, especially with TESS. So TESS has 27-day sectors. There's a lot of gaps, which makes it difficult to detect longer period things, a challenge that I'm sure a lot of you are familiar with. Stellar binaries are also challenging and expensive to find with RVs. So, and especially for Delta Scutis, which are often A or F type stars, these stars are often rapidly rotating and radial velocities can be especially challenging. So we're hoping to ameliorate this with pulsation timing. So our approach is to take 1,400 or 1,416 light curves with greater than 6 sectors, which is the amount that we find we need in order to be able to detect anything, of 2-minute cadence test data. And then we distill that to a sample of about 1,161 Delta Scuti pulsators. We divide the light curves into 5-day windows, and we estimate the phase in each window. And then we go through that by eye and get like a nice short list of phase modulation binaries. So from this short list, we can actually fit the phase modulation. So we develop a JAX-based model that uses Giacalone to solve the Keplerian orbit in order to fit the binary orbits to pulsation modulation or pulsation timing variations. So it's based on Maelstrom by Dan Hay over here. And it basically forward models the pulsation timing variations directly onto the light curve. So we can fit that and we can obtain all of the binary parameters. And it works on GPUs, it's great, and it fits in minutes. So this is really useful when you want to do something on a large scale. So from this technique, we get a catalog of 53 new binaries. And so here's some of the examples. So for some of the binaries, the orbital period is longer than the baseline of tests that we have. And so we can't necessarily form unique solutions, but we attempt to fit them nevertheless. But for 24 of the 53 binaries, we actually can come up with unique solutions. And so you can see there's a range of different eccentricities, mass functions, and periods represented in even just these 4. On the bottom left, we have an interesting PB2 system. So that's when both the stars are pulsating, and you can actually assign modes to one or the other star based on the fact that they have antiphased time delays. So that's what I've plotted over there. And this is like a histogram of the various different periods. You can see we represent a wide range of different periods. But of course, when we get farther out, we start to get limited by the fact that the baseline of TESS is not quite enough for most of the stars that we're studying. One of the highlights of our binary catalog is actually the star Alpha Pictoris, which is known to have binary, but the orbit for the binary has never been obtained because the star is so rapidly rotating that RVs are practically impossible. And so with the pulsation timing, we could actually obtain the orbit of Alpha Pictoris B, and we actually extended our fitting procedure in order to use the Hipparcos accelerations as well. So we were able to fit both the pulsation timing and the Hipparcos accelerations together. To my knowledge, I think this is the first time these two techniques have been used together, and it was great. We were able to get the inclination of the orbit, which allows us to get the component masses individually. And yeah, so this is a very exciting thing for the future as well. So another thing that we can do with these kinds of intermediate period binaries is we can look at the kinematics now that we have Gaia available to us, Gaia DR3. So these are called tumor diagrams, if you haven't seen them before. The y-axis is the tangential velocity, the x-axis is the transverse velocity relative to the galaxy. And basically, the way that you can think about it is the farther a star is away from the origin, the more likely it is to be older, an older star. And the closer it is to the origin, the younger it's likely to be. And so immediately we were able to say from this that there are some stars in our test sample, which is on the left over here. Oh, sorry. There are some stars in our test sample over here that are that look kinematically older than an A or F type star should be, which is maybe a main sequence lifetime of about 2 billion years. And this is a little suspicious. We also looked at the Kepler sample, and we found a couple stars that were actually a few stars that were consistent with membership in the thick disk, and one star which is actually consistent with membership in the halo. And so we think that what's going on here is that these are actually products of mass transfer. Basically, we had a late type star and orbited by a companion that was more massive. That companion ascended the red giant branch, stably transferred mass onto the later type star. That late type star now oscillates on the instability strip as a delta Scuti, and the companion is now a white dwarf. So we can actually go out and use other techniques in order to confirm this, but that's pretty exciting. So this is kind of a taste of what is yet to come with TESS, because as I mentioned earlier, since this technique is preferentially sensitive to longer period binaries and companions, as we get more and more TESS baseline, we can detect both longer period objects, but also lower mass objects. So in our catalog, we have objects all the way down to the bottom of the stellar limit. And I'm very optimistic that with additional baselines of TESS, we can definitely extend into the brown dwarf regime and likely also into the exoplanet mass regime. Of course, we can use full frame images. Now we have great full frame image cadence, which is great for this technique. And I mentioned earlier that this technique has great synergy with Gaia, or like generally astrometry. And so Gaia DR4 is going to be great. There's going to be lots of objects in DR4 that have poor astrometry, but that the pulsation timing will allow us to fit more, a lot better if the star is a pulsator. And of course, radial velocity follow-up of long period binaries is something that we can do for specific systems where the baseline of TESS isn't enough as well. And so with that, I'll put up my summary and conclusions, and I'm happy to take questions. Thank you.
Questions for Shishir? One in the middle. Next one at the front.
This is Nobkawai from Tech American. What is the prospect of finding invisible massive companion, namely non-accreting black hole, with this technique?
Yeah, that's a good question. If I understand correctly, what is the prospect of finding high mass companions or compact objects or something?
Yeah.
I think those are definitely accessible to this technique as well. Obviously, I think the statistics are low because TESS samples the brightest stars in the sky, but it doesn't go particularly deep. But that being said, if there are like compact objects, if there's neutron stars or black holes orbiting delta Scutis, then those would be in principle detectable with this technique, of course. Thanks.
Right at the front.
Hi, I'm Masafumi Niwano from Tokyo Tech. Is there any explanation about histogram, a valley in histogram of orbital period?
Yeah, that's a great question. Yes, there is an explanation, and that is that a lot of the stars are close or in the CVZs of TESS. And so the CVZs, of course, sample like for like a year, and then they go to the other side, and then they sample for a year again. So we have a gap in our period sampling where we also see a gap in most of our stars' TESS coverage, photometric coverage. And so hopefully that will be filled in with more TESS depending on the TESS mission strategy going forward. But yeah, that's kind of that's not astrophysical. That's an effect of our sampling, basically.
Thank you. Thanks.
Any further questions? I have one of my own.
Yeah.
How involved is it to fold in the fitting of the astrometry with the fitting of the pulsation timing?
It's not too involved, actually. Like, I'm planning to put my code up on GitHub, so you can all use it if you'd like. But yeah, with that, it'll definitely be very easy and very tractable. But we have to wait for DR4 to come out for that to be usable on a wider scale. But yeah, it should be in principle quite easy.
Any final questions? If not, let's thank Shishir again. This wraps up our session for today. Yes, and we will convene and start again tomorrow at 9 a.m. See you then.